Reference models are conceptual frameworks for understanding relationships. The purpose of the reference models are to guide vendors and developers so that digital communication products and software programs they create can interoperate and facilitate clear frameworks that describe the functions of a networking or telecommunication system. And finally, we're in the application layer. Now, if you remember, I mentioned before, for the ease of use, the last three layers, session layer, presentation layer, and application layer, are thought of together as the application layer. As you know, these three layers are already a single layer in the TCP/IP reference model. So the application layer contains the communications protocols and interface methods used in process-to-process communications across an Internet Protocol computer network. The application layer only standardizes communication and depends upon the underlying transport layer protocols to establish host-to-host data transfer channels and manage the data exchange in a client-server or peer-to-peer networking model. So let's have a look at some important protocols of the application layer. Okay, folks, we are at the end of the Network Fundamentals course. I certainly hope you've learned and enjoyed as much as I have. But before you go, let's have a brief summary. So first we talked about the basic terms. What is the Internet? What is the protocol? What does the internetwork look like when it's working? And all of this. Now, secondly, we looked at the reference models, OSI and TCP/IP reference models. Then we talked about each layer from bottom to top and the best known protocols of all of them. Then we looked at the data link layer and its protocols, Ethernet and ARP or ARP. And we also learned the virtual LANs and the wireless LANs in this layer. The network layer and IP protocol. We saw the two different versions of IP, subnet, private networks, network address translation, and DHCP in this section. The transport layer and TCP and UDP protocols. And finally, the application layer, DNS system, HTTP, and HTTPS protocols. So thanks again for choosing us, and we hope to see you in another course. So let's have a look at the network sniffing methods first. We're going to learn how to listen to the network traffic and how to use some tools such as TCP dump and Wireshark. During the penetration test, we listened to the network traffic for many good reasons. First of all, it's possible to obtain the clear text critical information, such as usernames, passwords, instant messages, emails, and all that. We can check to see if the scans work correctly. And some controls can be seen by listening to the network interface, such as if the scan parameters are set correctly, packets are properly exported from the network interface, and responses are received. Listening to the traffic, using passive scan methods, we can collect information about IP addresses, services running on server systems, and protocols and technologies used in network infrastructures, etc., etc. So I bet you're hoping to learn how to prevent MAC flooding attacks, and you've come to the right place. To prevent the MAC flooding attacks, network operators usually rely on the presence of one or more features in their network equipment. With a feature often called port security by vendors, many advanced switches can be configured to limit the number of MAC addresses that can be learned on ports connected to end stations. Many vendors allow discovered MAC addresses to be authenticated against an authentication, authorization, and accounting or AAA server, and subsequently filtered. Implementations of IEEE 802.1x suites often allow packet filtering rules to be installed explicitly by a AAA server based on dynamically learned information about clients, including the MAC address. Security features to prevent ARP spoofing or IP address spoofing, in some cases, may also perform additional MAC address filtering on unicast packets. However, this is an implementation-dependent side effect. So here are the basic principles of the switch ports. The ports of a switch is in dynamic desirable mode by default. If the device connected to the port is a computer, the mode of the port becomes access, and the port is dedicated to that computer. If the device is another switch, the mode of the port becomes trunk. So by default, trunk ports have access to all VLANs and pass traffic for multiple VLANs across the same physical link, generally between switches. So switch spoofing is a type of VLAN hopping attack that works by taking advantage of an incorrectly configured trunk port. In a switch spoofing attack, the network attacker configures a system to spoof itself as a switch. So this spoofing requires that the network attacker be capable of emulating 802.1q and DTP messages. By tricking a switch into thinking that another switch is attempting to form a trunk, an attacker can gain access to all the VLANs allowed on the trunk port. So the best way to prevent a basic switch spoofing attack is to turn off trunking on all ports, except the ones that specifically require trunking. On the required trunking ports, disable DTP, Dynamic Trunking Protocol, and manually enable trunking. So you can either use radius servers or the local functions of the switches to manage the users. It is advised to use the central identity management approach. And here's some more advice for identity management. Create a different account for every user. Identify the user in the same center. Create and apply a central password policy for all users. And change the passwords periodically. If you use local user management functions, you should follow the same policies as I just explained. However, it's much harder to manage the users and the policies because, random. So let's look at the basic concepts of networking and, of course, the mother of all networks, the Internet. The Internet is a global system of interconnected computer networks that use the standard Internet Protocol Suite, often called TCP/IP, although not all applications use TCP, to serve billions of users worldwide. It's a network of networks that consists of millions of private, public, academic, business, and government networks of local to global scope that are linked by a broad array of electronic, wireless, and optical networking technologies. The Internet carries an extensive range of information resources and services, such as the interlinked hypertext documents of the World Wide Web, WWW, and the infrastructure to support email. The origins of the Internet reach back to research done in the 1960s, commissioned by the United States government in collaboration with private and commercial interests to build robust, fault-tolerant, and distributed computer networks. The primary precursor network, the ARPANET, initially served as a backbone for interconnection of regional academic and military networks in the 1980s. The funding of a new U.S. backbone by the National Science Foundation in the 1980s, as well as private funding for other commercial backbones, led to worldwide participation in the development of new networking technologies and the merger of many networks. The commercialization of what was by the 1990s an international network resulted in its popularization and incorporation into virtually, I'd say, every aspect of modern human life. So as of 31st December 2017, more than 4.1 billion people, nearly 55% of the whole world population, use the services of the Internet. Now, I'll put that in a little perspective here. That's 95% of North Americans and about 85% of Europeans are Internet users. Now, before talking about the Internet protocol, or what we call IP. We should know what a protocol actually is. A protocol is simply a set of rules governing how things work in a certain technology, so that there is some kind of standardization. Protocols are also typically in charge of sending the right data to the right PC, making sure the data gets to the right program, as well as organizing the data to be sent. Protocols are to computers what language is to humans. For instance, this course is in English. To understand it, you must be able to understand English. So similarly, for two devices on a network to successfully communicate, they must both understand the same protocols. So I know we're going to talk about this in detail later, but we'll talk a little bit now about IP to better understand the Internet. Internet Protocol, IP, describes how data packets move through a network. So when you have a protocol, you are sure that all machines on a network, or in the world when it comes to the Internet, however different they might be, speak the same language and can integrate into the whole framework. The IP protocol standardizes the way machines over the Internet or any IP network forward or route their packets based on their IP addresses. So along with addressing, routing is one of the main functions of the IP protocol. Routing consists of forwarding IP packets from source to destination machines over a network based on their IP addresses. An IP address is a unique address identifying a machine, which can be a computer, a server, an electronic device, a router, a phone, you name it, on a network, thus serving, routing, and forwarding IP packets from source to destination. Basically, every computer connected to the Internet is given an IP address by the Internet service provider, and the computer becomes accessible to others via this IP address. So let's see what the Internet looks like on its most basic level. Here we have a home network with a router given by the Internet service provider, or ISP. Remember that modem that's given to you by your ISP, and the devices it connects to the Internet. This is a corporation with a lot of end-user computers and servers as well. There's a public body here, again, with a lot of servers and a lot of end-user computers. Here is a hosting company with a web server farm hosting to their customers. Now here's a cloud provider such as Amazon Web Services, hosting a lot of servers again. And here there's another home, and they're all connected to each other over telecom company routers. OSI, Open Systems Interconnection, is a reference model for how applications can communicate over a network. A reference model is a conceptual framework for understanding relationships. The purpose of the OSI reference model is to guide vendors and developers so that the digital communication products and software programs they create will interoperate and to facilitate clear comparisons among communications tools. Most vendors involved in the telecommunications make an attempt to describe their products and services in relation to the OSI model. And although useful for guiding discussion and evaluation, OSI is rarely actually implemented, as few network products or standard tools keep all related functions together in well-defined layers as related to the model. Developed by representatives of major computer and telecommunication companies beginning in 1983, OSI was originally intended to be a detailed specification of actual interfaces. Instead, the committee decided to establish a common reference model for which others could then develop detailed interfaces, which in turn could become standards. OSI was officially adopted as the international standard by the International Organization of Standards, ISO. So what about the OSI layers? The main concept of OSI is that the process of communication between two endpoints in a telecommunication network can be divided into 7 distinct groups of related functions, or layers. each communicating user or program is at a computer that can provide those 7 layers of function. So, in a given message between users, there will be a flow of data down through the layers in the source computer, across the network, and then up through the layers in the receiving computer. The 7 layers of function are provided by a combination of applications, operating systems, network card device drivers, and networking hardware that enable a system to put a signal on a network cable or out over Wi-Fi or any other wireless protocol. The 7 open systems interconnection layers are: Layer 7, the application layer. This is a layer at which communication partners are identified. Is there someone to talk to? Network capacity is assessed. Will the network let me talk to them right now? And it creates a thing to send or opens the thing received. Please note that this layer is not the application itself. It is the set of services an application should be able to make use of directly, although some applications may perform application layer functions. Layer 6, the presentation layer. This layer is usually part of an operating system and converts incoming and outgoing data from one presentation format to another. For example, from clear text to encrypted text at one end and back to clear text at the other. Layer 5, the session layer. This layer sets up, coordinates, and terminates conversations. Services include authentication and reconnection after an interruption. On the Internet, Transmission Control Protocol, TCP, and User Datagram Protocol, UDP, provide these services for most applications. Layer 4, the transport layer. This layer manages packetization of data, then the delivery of the packets, including checking for errors in the data once it arrives. On the Internet, TCP and UDP provide these services for most applications as well. Layer 3, the network layer. This layer handles the addressing and routing of the data, sending it in the right direction to the right destination on outgoing transmissions, and receiving incoming transmissions at the packet level. IP is the network layer for the Internet. Layer 2, the data link layer. This layer sets up links across the physical network, putting packets into network frames. This layer has 2 sublayers, the logical link control layer and the media access control layer. Ethernet is the main data link layer in use. Layer 1, the physical layer. This layer conveys the bit stream through the network at the electrical, optical, or radio level. It provides the hardware means of sending and receiving data on a carrier network. Let's see some of the most famous protocols of the layers. For ease of use, it's better to talk about physical layer and data link layer together. Here we have some protocols in data link layer and some physical media and connection methodologies in physical layer. Ethernet and 802.11 wireless LAN are the most known protocols of the data link layer. Ethernet is the name of the most commonly used network protocol that controls how data is transmitted over a LAN, which is a local area network. You need to have network interface cards in the devices that you want to connect to the network. A wireless local area network, WLAN, is a wireless computer network protocol that links 2 or more devices using wireless communication within a limited area such as a home, school, computer laboratory, or office building. This gives users the ability to move around with a local coverage area and yet still be connected to the network. Most modern WLANs are based on IEEE 802.11 standards and are marketed under the Wi-Fi brand name. IP, Internet Protocol, is responsible for addressing hosts, encapsulating data into transferred packets, and routing packets from a source host to a destination host across 1 or more IP networks. The best-known transport protocol is the Transmission Control Protocol, or TCP. It's used for connection-oriented transmissions, whereas the connectionless User Datagram Protocol, UDP, is used for simpler messaging transmissions. We're going to talk more in depth about these protocols in the next lecture. Again, for ease of use, The last three layers, session layer, presentation layer, and application layer, are thought of together as the application layer. Let me put another parenthesis here. We're talking about the OSI reference model here. In addition, there is another reference model called TCP/IP reference model. And instead of OSI model's last three layers, there is only a single application layer in the TCP/IP reference model. Just keep that in the back of your mind. And back to our subject. The application layer protocols are classified according to the protocol they are using in the transport layer. And these protocols interact with the end user via applications. Therefore, they are the most known protocols by just about everybody. Some of the most well-known TCP-based application layer protocols are HTTP, Hypertext Transfer Protocol, simply a communications protocol used to send and receive web pages and files on the Internet. Telnet is one of the simplest ways to exchange data between two computers. It allows two computers anywhere on a computer network, including the worldwide Internet, to exchange text and, other data in real time. FTP, File Transfer Protocol, is a communication protocol for the rapid, simple transmission of files across a network. SMTP, Simple Mail Transfer Protocol, is used to send and relay an email message between email servers. Note that it is not used to retrieve email messages from a server. Instead, either IMAP or POP is used to retrieve email messages. DNS, the Domain Name System, is a system used to convert a computer's host name into an IP address on the Internet. For example, if a computer needs to communicate with a web server nhs.uk, your computer needs the IP address of the web server nhs.uk. It is the job of the DNS to convert the host name to the IP address of the web server. The DNS uses both the UDP and TCP. SNMP, Simple Network Management Protocol, is used in network management systems to monitor status of devices and also spot problems. So let's see what happens to a packet inside the network traffic. Please note, the data unit transferred between two endpoints has different names in each layer. In layers 5, 6, and 7, application layers, it's called data. In layer 4, transport layer, it's called segment for TCP and datagram for UDP. In layer 3, the network layer, it's called packet. In layer 2, the data link layer, the data unit is called frame. Now, I usually use packet for the transferred data unit in each layer to make it less complicated for you. Make sense? Before looking at the road trip of a DNS query in detail, let's look at the relationship between the OSI layers and computer systems. The packets in Layer 1 and Layer 2 are managed by network interfaces of your device, for example, by your Ethernet card. And the packets from 3 to 7 are managed by the processing unit. In software detail, the Layer 3 and Layer 4 packets are managed by the operating system of your devices. And the packets of Layer 5 to 7 are managed by the related application or service, for example, a web browser. When you write a URL in the address bar of your browser and hit Enter, the first thing it sends is a DNS query. A DNS query is the process of a computer or networking device making an inquiry to get an IP address for a DNS name such as mail.yahoo.com. The client computer will send a DNS query to one of their Internet Service Provider's DNS servers. The DNS server looks in its DNS database to tell whether it can answer the query authoritatively. If the DNS server can answer authoritatively, the DNS server answers the query and the DNS query process is complete. So let's see the road trip of a DNS query from your computer to a DNS server. When data is transmitted by the source toward a specific destination, it passes through the application, presentation, and session layers, and the protocol data unit arrives at the transport layer, Layer 4. Layers 5, 6, and 7 are displayed as a single layer to simplify the presentation. At this layer, a 20-byte data header is placed in front of the data. A DNS query can also use TCP, But let's assume that it uses UDP at this time. The data and the layer 4 header, here it's UDP header, which together form a segment or datagram, is passed down to layer 3, the network layer. The network layer places its layer 3 header, here the IP header, in front of the received segment, and this group becomes a packet. The layer 3 header contains important fields such as the logical address, the IP address, of both the source and the destination device. The newly formed packet is then passed down to layer 2. The data link layer creates a new data unit called a frame by adding the layer 2 frame header, which is the Ethernet header here. Like layer 3, an addressing structure is also applied in the layer 2 header. That is, the MAC address. The frame is then passed down to the physical layer, which converts the information into 0 and 1 bits that are sent over the physical media using electrical signals, on a copper link, for instance. Finally, the data is sent over the wire using a wide variety of methods such as Ethernet or token ring. The headers are a specific form of control information that allows the data to go through the network properly. Thus, the data at each layer is encapsulated in the information appropriate for the specific layer, including addressing and error checking. The overall size of the information increases as the data travels through the lower layers from layer 4 to layer 1. The destination device, which is the DNS server here, receives the data, and this additional information is analyzed and then is removed as the data passes through the higher layers up to the application layer, where the data is decapsulated. The physical address, commonly the MAC address, which is located in a special field in the data link layer header, changes as the packet passes from one device to another. For example, from the source PC to a switch to a router to another switch and finally to the destination PC. However, the original IP source and destination addresses do not change when transiting the network because the packet is stripped of its layer 3 header only when it goes beyond a router. When it stays within the same LAN, it only passes through switches which decapsulate it at the layer 2 header containing the MAC address. As a result, the header changes as the packet is re-encapsulated, as does the MAC address fields. The TCP/IP model is a model with 4 layers, which is for both modeling current Internet architecture, as well as providing a set of rules that govern all forms of transmission over a network. DARPA, an agency of the United States Department of Defense, created it in the 1970s. This model was being made at the same time the OSI model was created. The TCP/IP model is not the same as the OSI model, however. It was influenced by the model, which is why many of the names of the different layers are the same. So we can simply say that the TCP/IP reference model represents reality in the real world, whereas the OSI reference model represents an ideal. Okay? So these are the main differences of the TCP/IP reference model. The 3 top layers in the OSI model, that is the application layer, the presentation layer, and the session layer, are not distinguished separately in the TCP/IP model, which only has an application layer above the transport layer. TCP corresponds to OSI layer 4, the transport layer. IP corresponds to a subset of OSI layer 3, the network layer. TCP/IP makes no prescriptions as to the link layers below IP, while OSI specifies 2 layers. The physical address, commonly the MAC address, which is located in a special field in the data link layer header, changes as the packet passes from one device to another. For example, from the source PC to a switch, to a router, to another switch, and then finally to the destination PC. However, the original IP source and destination addresses do not change when transiting the network because the packet is stripped of its layer 3 header only when it goes beyond a router. When it stays within the same LAN, it only passes through switches, which decapsulate it at the layer 2 header containing the MAC address. So as a result, the header changes as the packet is re-encapsulated, as does the MAC address fields. So let's examine the packets and protocols with Wireshark. Wireshark is a free, open source, and it's the world's foremost network packet analyzer. And it's also the de facto standard across system and network administrators. Wireshark has the ability to listen and record traffic, as well as contains some pretty advanced filtering and reviewing options. So first I'm going to visit an HTTP website and then an HTTPS website. Let's go to Kali and run Wireshark. You can open a terminal screen and type Wireshark to start it. So these are the network interfaces that Wireshark is able to listen to. Let me open another terminal screen and run the ifconfig command to see the network interfaces. So as you know, ifconfig stands for network interface configuration. So if we use the command without any parameter, it'll list all the interfaces available. We have eth0 as a network interface to listen to. So now I'll turn back to Wireshark and double-click eth0 to select it. Now Wireshark starts to listen to the Ethernet interface of Kali. And to create some traffic, I'll open a web browser and just visit an arbitrary website. And now we have enough packets to examine, so I'll click the Stop button at the upper left corner of Wireshark to stop listening to the traffic. So first, we have some DNS packets to find out the IP address of the visited site. We'll look at these kinds of packets soon, but right now let's just have a brief look. So a DNS query for the IP version 4, another DNS query for IP version 6. Don't worry about the versions right now. We'll cover them soon, I promise. These DNS queries are transferred as UDP packets in transport layer. The destination port is 53. This is the IP packet with the source and the destination IP addresses. So we'll go through the layers one by one, and we'll see all these packets, datagrams, and frames in detail. So we'll keep going. This is the structure of the Ethernet frame. First, there are two DNS queries for www.hackeracademy.uk. One for the IPv4 address, and the other one is for the IPv6 address. And because the website is redirected to hackeracademy.uk, there are two more DNS requests for this address. Next, DNS packets are the DNS query responses. This response is type A. That means it's an answer for the IPv4 request. And here's the answer, the IP address of the website. Now, DNS response packet uses UDP at the transport layer, IP at the network layer, etc. Here we have a TCP handshake between Kali and the web server. We'll also see this in detail later on. A SYN packet, a SYN ACK as a reply, and an ACK packet to complete the handshake. This is an HTTP GET request. We learned the IP address of the website, and now the system is ready to receive the web page. HTTP protocol and application layer. Now you can see the headers and the parameters of the request. TCP protocol and transport layer, source port, destination port, flags, etc. IP protocol in network layer. Here are the source and destination addresses. And Ethernet frame in layer 2. These are the TCP packets, which will build the HTTP response. So in this example, it's the web page. In other words, the response is transferred between the web server and our system as fragmented packets in transport layer. Here's the HTTP response, 200, okay, so the web page is received. And here's the data, which is our web page. These are the response details, response type, headers, etc. Here there's additional information produced by Wireshark, which says that the HTTP response is created by reassembling 5 TCP segments or packets. So now I'd like to show you the difference between that and HTTPS traffic. So I'll go to the browser and visit an HTTPS page now. But before visiting the page, let's start Wireshark. Here's the start button. Continue without saving. Okay, now we have a clean sheet. So I'll go to the browser and hit enter. Wow, lots of packets in milliseconds. So we've got plenty of packets to investigate. Just click the stop button once again. Okay, so the DNS request and the response packets first. Here is a response with an IPv4 address. Here there's a TCP three-way handshake between Kali and port 443 of Google's web server. And now a client hello TLS packet to start the TLS handshake, again between Kali and Google's server. Now to get rid of the other traffic records, I'd like to filter the results by the IP address of the Google server. Now, while the mouse pointer is on the server IP address, right-click and go to Apply as Filter and select the Selected option. So as you can see here in the filter bar, the IP address is assigned as the destination IP address. Now, we only have to see the traffic where the destination is the Google server. But we'd like to see both the incoming and the outgoing traffic. So I'll change the DST part of the filter to ADDR and click the blue arrow to activate the new filter. Now we can see the traffic in both directions. Okay, so here we are at the Hello TLS message. Here are the details of the message. TLS uses TCP protocol in transport layer. The Google server replies a server hello message as the second step of the TLS handshake. Then comes the certificate and server key exchange, and the server hello done message is sent by the server. Kali sends the client key exchange, Google server sends the new session ticket, and the encrypted communication starts. Here is some encrypted application data, which is meaningless for others who listen to the traffic. And as you can see here, the message is encrypted at the application layer, so you can still see the source and the destination addresses, the ports, etc. All right, so since there's really nothing much to say about the physical layer, because in this course we're really looking at the digital side of networking, I'd like to just skip that and start with the second one, the data link layer. The data link layer is the second layer in the OSI, Open Systems Interconnection, 7-layer reference model. Now, it responds to service requests from the network layer above it and issues service requests to the physical layer below it, right? So the data link layer is responsible for encoding bits into packets prior to transmission and then decoding the packets back into bits at the destination. And bits, by the way, are the most basic unit of information in computing and communications. Packets are the fundamental unit of information transport in all modern computer networks, and increasingly in other communications networks as well. So the data link layer is also responsible for logical link control, media access control, hardware addressing, error detection, and handling and defining physical layer standards. It provides reliable data transfer by transmitting packets with the necessary synchronization, error control, and flow control. The data link layer is divided into two sublayers. First, the media access control, MAC, sublayer, that governs protocol access to the physical network medium. Through the MAC addresses that are typically assigned to all ports on a router, multiple devices on the same physical link can uniquely identify one another at the data link layer. MAC addresses are used in addition to the network addresses that are typically configured manually on ports within a network. Now, secondly, the logical link control, or LLC sublayer, manages communications between devices over a single link of a network. This sublayer supports fields in link layer frames that enable multiple higher layer protocols to share a single physical link. So here we have some protocols in the data link layer and some physical media and connection methodologies in the physical layer. Ethernet and 802.11 wireless LAN are the best-known protocols of the data link layer. Ethernet is the name of the most commonly used network protocol that controls how data is transmitted over a LAN, which is a local area network. Now, you need to have a network interface card in the device that you want to connect to the network. I know it probably seems pretty obvious to you, but I just wanted to make sure that we're all on the same page. A wireless local area network, or WLAN, is a wireless computer network protocol that links two or more devices using wireless communication within a limited area, such as a home or school, computer lab, or office building. Now, this gives users the ability to move around within a local coverage area and still be connected to the network. Most modern WLANs are based on the IEEE 802.11 standard and are marketed under the Wi-Fi brand name. So Ethernet has been a relatively inexpensive, reasonably fast, and very popular LAN technology for, several decades. It was commercially introduced in 1980 and first standardized in 1983 as IEEE 802.3. And has since been refined to support higher bit rates and longer link distances. Ethernet has since become the most popular and probably the most widely deployed network technology in the world. Many of the issues involved with Ethernet are common to many network technologies, and understanding how Ethernet addresses these issues can build a foundation that will improve your understanding of networking in general. So let's keep the design principles of Ethernet simple. The basic idea of its design is that multiple computers have access to it and can send data at any time. If two computers send data at the same time, a collision will occur. And when this happens, the data sent is not going to be usable. In general, both computers will stop sending and wait a random amount of time before they'll try again. Now, a special protocol was developed to deal with such problems. It's called Carrier Sense Multiple Access with Collision Detection, or it might be easier to say CSMA-CD. Today, Ethernet cables look like, thick telephone cables. Modern cables connect to hubs or switches, and each cable runs from a computer's network interface card, the NIC, to such a box. Now, here are the most widely known Ethernet cables. 10-base-2 and 10-base-5 cables are what I would call retro coaxial cables. You don't see them much today. Each computer has a T plugged into it, and cables plug into each side of that T. 10-base-T, 100-base-T, 1000-base-T are all unshielded twisted pair, or UTP cables, which look a lot like thick phone cables, and they go from each computer to a hub or a switch. Initial numbers indicate the supported speed, so the 10 will stand for 10 megabits per second, and 1000 stands for 1000 megabits, also known as gigabit or 1 gigabit. 10-base-F cables are the same as 10 base T, but they are fiber cables, and they'll transmit light pulses instead of electrical signals over copper. A data packet on an Ethernet link is called an Ethernet packet, which transports an Ethernet frame as its payload. An Ethernet frame is preceded by a preamble and start frame delimiter, or SFD, which are both part of the Ethernet packet at the physical layer, right? There are 4 types of Ethernet frames, and the most common one is the Ethernet 2 frame, also known as DICS frame. We're talking about the Ethernet 2 frame at the moment. Each Ethernet frame starts with an Ethernet header, which contains destination and source MAC addresses as its first 2 fields. The middle section of the frame is payload data, including any headers for other protocols, for example, Internet Protocol, carried in the frame. The frame ends with a frame check sequence, or FCS, which is a 32-bit cyclic redundancy check used to detect any in-transit corruption of data. Address Resolution Protocol, ARP, is a network layer protocol used for mapping a network address such as an IPv4 address to a physical address such as a MAC address. To simulate how the ARP mechanism works, we have a small network in the slide, a switch on top, and 3 computers connected to it. Computer A wants to talk to computer C. It puts an ARP request onto the wire, which happens to be broadcast. Essentially what it's saying is, who has computer C's MAC address? Of course, because it's a broadcast, every system on the network hears it. Does everybody respond? Well, what happens is that B hears that A is looking for the MAC address of computer C. B knows that it's not computer C and therefore does not respond to the broadcast. The broadcast, the ARP request, goes out to every system, but the only system that will reply is computer C with an ARP reply. In other words, computer A says, who has the MAC address of computer C? And although all the workstations hear the question, only C replies and says, I've got the MAC address of computer C, and this is what it is. So the ARP reply sends back the MAC address to computer A, and each of these machines start building an ARP table. So what is the ARP table? Since computers cannot send broadcast messages every time they need to connect with another network device, they store the IP addresses and the corresponding MAC addresses of systems they frequently communicate with in a table called ARP table. All the systems in the LAN maintain this table. The entries in the ARP cache table are generally short-lived and are updated every 15 to 20 minutes. Now let's get back to our topic. Can we say that one of the passive scan methods is just looking into the ARP table of a system, which is a network that we are scanning? Well, sure we can. Inside an ARP table, we see the IP addresses of some of the systems of the network and their corresponding MAC addresses. Let's see the ARP tables in 3 different platforms: Mac OS, Windows, and Debian Linux. We are in a Mac OS operating system first. Open the terminal first. Type terminal in the search box of the applications window, which brings you the terminal application. Typing ARP and hitting enter shows a small help for ARP command. If you want to see detailed help about the ARP command, you can use MAN command. Type MAN ARP and hit enter. You'll get detailed help. A parameter is used to display all current ARP table entries. But hold on, it says A is used to delete all entries as well. How can that be? Well, to delete an ARP table entry, you use D parameter. If you use this parameter with A parameter, you are able to delete all entries of ARP tables. I parameter is used to see the entries of a single interface. By default, ARP command tries to show the display addresses symbolically. To see the IP addresses instead of display names of the systems, you have to use N parameter, which means do not resolve names. Okay, press Q to quit the man page of the ARP command. Now type ARP-AN to see all the entries of the ARP table. Since macOS is a BSD-based operating system, the results of the ARP command is displayed in BSD style. Second machine is a Microsoft Windows 8. Let's open a command prompt first. I have a shortcut on my status bar, so I click it to start a command prompt. Alternatively, press Windows plus R buttons, open the dialog box, run Command, and hit Enter. If you type ARP in a Windows system, the help page of ARP command is displayed. Type ARP-A to see the entries of the ARP table. In my opinion, this display is more, human readable than BSD style. Now, although we're not interested in these at the moment, I would like to talk a little about the IP addresses that start with 224 to calm your curiosity. 224.0.0.22 is the multicast address for Internet Group Management Protocol. 224.0.0.252 is used by recent versions of Windows for Link Local Multicast Name Resolution, LLMNR, searching for local network computers. The third machine is our Kali, which is a Debian-based Linux operating system. Open the terminal window. If you type ARP and hit Enter, the ARP table entries are displayed in a human-readable format. As you see, systems are listed with a known domain name such as www.owaspbwa.com by default. ARP-H brings you a small help page. If you want a detailed help page, type man space ARP. In a Debian-based Linux system, -A parameter of ARP command is used to see the entries in BSD format, which we saw in macOS. -I is, again, to see the entries of a single interface. Okay, press Q to quit the man page. ARP-A displays ARP table entries in BSD format, and use N parameter to see the IP addresses instead of domain names of the systems. So let's see how the ARP packets are seen in Wireshark. To see the ARP packets, we must first force the system to send an ARP request. Then we can have a close look into the fields of the ARP packets. So I'm in Kali, and I want to look at the ARP table first. So I'll open a terminal browser and type ARP. So this is the ARP table of my Kali. There are two records at the moment, one for the gateway and one for the VM with the IP address of 207. So let's clear the table first. Now I don't have to delete the records of the ARP table, so I can use the H parameter to get help. So it tells me to use the D parameter to delete a specified entry. Now, does it delete all the entries if I don't specify any particular one? So I'll use the D parameter with no value, and it needs the host name. Okay, so I delete the entry for VM207, so I can push it to create an ARP request. Okay, deleted the entry. Now I'll run Wireshark. Now remember, we run Wireshark within the terminal screen just as before. So I'll click Wireshark icon, and that makes it run. So double-click the ETH0 to start capturing the traffic. Okay, now I'll go to the terminal screen and ping VM207. Turn back to the Wireshark interface, and since we have enough packets to examine, let me just stop capturing. So let's look at the first packet. It's an ARP request. When we ping the IP address 172.16.99.207, since Kali doesn't know who has this address, it broadcasts an ARP request to learn the owner of the IP. And the second packet is an ARP response. So I go back to the request and expand the ARP packet information block. The sender MAC address and the sender IP address are Kali's addresses. The target MAC address is filled with zeros because, well, we don't know it yet. When we look at the Ethernet frame, we see that the 48-bit destination address is full of ones. All these F letters correspond to these ones in hexadecimal, and the frame is broadcast, right? Now this is the ARP response by VM207. And as you can see, the VM returns its MAC address in the sender MAC address field to Kali. And then, as seen in the table, Kali starts to send the ping requests to VM207. And then VM207 replies to the requests. Talk about clear communication. So before talking about VLANs, I think it's better to give a brief summary of LANs in general. So a LAN is a local area network. It's a group of computers and associated devices that share a common communications line or wireless link to a server. Typically, a LAN encompasses computers within a distinct geographic area, such as an office or a commercial establishment. Computers and other mobile devices use a LAN connection to share resources, such as a printer or even network storage. A virtual local area network, virtual LAN or VLAN, is a group of hosts with a common set of requirements which communicate as if they were attached to the same broadcast domain, regardless of their physical location. So a VLAN has the same attributes as a physical local area network, or LAN, but it allows for end stations to be grouped together even if not on the same network switch, right? VLAN membership can be configured through software instead of physically relocating devices or connections. VLAN is an important topic and it should be included in this course, but why did I put it in this section, the data link layer? Yes, because VLAN is partitioned and isolated in a computer network at the data link layer. Very good. Let's get into that. In this context, virtual refers to a physical object recreated and altered by additional logic. VLANs work by applying tags to network packets and handling these tags in networking systems, creating the appearance and functionality of network traffic that is physically on a single network but acts as if it is split between separate networks. So let's run down some of the primary benefits of using VLANs. So security at the top. Groups that have sensitive data are separated from the rest of the network. Separating systems that have sensitive data from the rest of the network decreases the chances that people will gain access to the information that they're not authorized to see. Cost reduction. Cost savings result from less need for expensive network upgrades and more efficient use of existing bandwidth and uplinks. Higher performance. Careful monitoring of network use allows the network administrator to create VLANs that reduce the number of router hops and increase the apparent bandwidth for network users. Broadcast storm mitigation. So dividing a network into VLANs reduces the number of devices that may participate in a broadcast storm. Since a principal element of a VLAN is the fact that it does not pass broadcast traffic to nodes that are not part of the VLAN, it automatically reduces broadcasts. Improved IT staff efficiency. That's right, VLANs make it easier to manage the network. When you provision a new switch, all the policies and procedures already configured for the particular VLAN are implemented when the ports are assigned. Simpler company management. Companies may want VLANs set up for departments that are heavy network users, such as multimedia or engineering, or a VLAN across departments that is dedicated to specific types of employees, such as managers or salespeople. Excellent. So a wireless network is a computer network that uses wireless data connections between network nodes. Wireless networks are generally implemented and administered using radio communication. And with this method, the costly process of introducing cables into a building can, well, obviously be avoided. A wireless local area network, WLAN, links two or more devices over a short distance using a wireless distribution method, usually providing a connection through an access point for internet access. IEEE 802.11 is a set of MAC and physical layer specifications for implementing wireless LAN computer communication. Now, they're the world's most widely used wireless computer networking standards, used in most home and office networks to allow laptops, printers, smartphones to talk to each other and access the internet without being connected to any wires. So for this, I'm just trying to keep it simple, so I won't talk about the entire 802.11 family or the technical details beneath them. I just want to let you know that the most popular are those defined by the 802.11b and the 802.11g protocols, which are amendments to the original standard. So 802.11-1997 was the first wireless networking standard. But 802.11b was the first widely accepted one, followed by 802.11g and then 802.11n. 802.11n is an amendment that improves upon the previous 802.11 standards by adding multiple input, multiple output antennas, MIMT. So MIMT, it's basically a method for multiplying the capacity of a radio link using multiple transmit and receive antennas. Nowadays, 802.11ac is popular. So it builds on the 802.11n and includes wider channels in the 5 gigahertz band. The segment of the radio frequency spectrum used by 802.11 varies pretty much between countries. For example, in the U.S., 802.11a and 802.11g devices may be operated without a license, as allowed in the regulations. Wireless networks are identified using a Service Set Identifier, or SSID, or I'll call it a SID. An SSID is the primary name associated with an 802.11 wireless LAN, including home networks and public hotspots. Client devices use this name to identify and join wireless networks. Now, there are multiple kinds of SSIDs. Used by itself, the term SSID refers to the name of a wireless network, whether it be a point-to-point network made of only individual wireless clients intercommunicating, or an infrastructure network with clients relying on access points. So getting more specific, we have basic SSIDs, or BSSIDs, which are the MAC address of the access point, the 48-bit number that uniquely identifies every wireless, and every wireline for that matter, network interface. The extended SSID, or ESID, is a unique name applied to one or more access points offering the same service, such as access to a single wireline network. Now, in some deployments, unique ESIDs are applied to each individual access point. In others, all access points that offer access to the same wireline network are given identical ESID values to help foster roaming between the various access points. But generally speaking, when analyzing wireless LANs, we want to discover the BSSID, the MAC address, and the ESID, the name applied to the wireless network as a whole, with a unique value typically applied to each individual access point. Now, since this is a course for penetration testers, we really need to talk about the weaknesses of the wireless network infrastructure. So here are some of the most significant vectors for wireless attacks. Denial of service. Blocking legitimate users on a wireless LAN is trivially easy, even if the network is carefully constructed. rogue access points. Employees sometimes set up unauthorized access points in an enterprise environment to bypass the legitimate wireless infrastructure or to gain wireless access when such an infrastructure isn't provided by the enterprise. Now, penetration testers and ethical hackers alike are sometimes required to sweep an organization's physical infrastructure to find these unauthorized access points. Lack of or improper configuration of wireless access points. Right, so if access points are not configured appropriately, attackers can have a much easier time of employing any of the rest of these attack vectors. Traffic capture intercept. In a wireless LAN, the hacker can get access to the data link layer 2 communications, as long as he or she is in physical proximity of the device. For merely capturing packets, that proximity for a wireless LAN could be a mile or more. Numerous wireless sniffing tools can be used in such attacks. Crypto attacks. Some wireless encryption protocols suffer from significant security weaknesses, such as the Wired Equivalent Privacy (WEP) protocol. Attackers can gather web traffic and, by exploiting flaws in the way cryptographic initialization vectors are exchanged, crack the keys to gain access to the data and the network. Client duping. Some tests call for a penetration tester or ethical hacker to set up a bogus access point to see if clients will trust it and then use it to access the rest of the network. The attacker can then sit in the middle of all the communications, harvesting them or changing the data as it passes by. The next layer is the third layer of the OSI reference model, the network layer. The network layer provides the means of transferring variable length network packets from a source to a destination host via one or more networks. In other words, the network layer is responsible for packet forwarding, including routing, through intermediate routers. Within the service layering semantics of the OSI network architecture, the network layer responds to the service requests from the transport layer and issues service requests to the data link layer. So here are the functions of the network layer. Connectionless communication. For example, IP is connectionless in that a data packet can travel from a sender to a recipient without the recipient having to send an acknowledgement. Connection-oriented protocols exist at other higher levels of the OSI model. Host addressing. Every host in the network must have a unique address that determines where it is. On the internet, addresses are known as IP addresses, right? Message forwarding. Since many networks are partitioned into subnetworks and then connect to other networks for wide area communications, networks use specialized hosts called gateways or routers to forward packets between networks. Probably the most well-known network layer protocol is, of course, IP or Internet Protocol. As I mentioned in the beginning of the course, the Internet Protocol, or IP, is responsible for addressing hosts, encapsulating data into packets or datagrams, including fragmentation and reassembly, and routing packets from a source host to a destination host across one or more IP networks. So like other Layer 3 protocols, IP is connectionless, which means it doesn't care whether the packet has reached the destination or not. That's what Layer 4 is for. All right? So there are two versions of IP that currently coexist within the global Internet. IP version 4, or IPv4, and IP version 6, or IPv6. IP addresses are made up of binary values and drive the routing of all data over the Internet. IPv4 addresses are 32 bits long, and IPv6 addresses are 128 bits long. Right now, we're going to see each of the versions in detail. But before we move on, let's compare the main features of each version. IPv4 is a 32-bit address, and IPv6 is a 128-bit address. Now, theoretically, you can address 2 to the power of 32 devices in IPv4, which is about 4.3 billion, right? In IPv6, on the other hand, you can address 2 to the power of 128 devices, which is, well, let's see. Why don't you just do the math on your own? So IPv4 is represented by the decimal equivalent of 4 octets, separated by dots. The biggest number one can make with 8 binary digits is 2 to the power of 8 minus 1, which means 255. So each octet can be any number from 0 to 255, right? Now, 128-bit IPv6 addresses are written using hexadecimal, as opposed to dotted decimal in IPv4. So because a hexadecimal number uses 4 bits, this means that an IPv6 address consists of 32 hexadecimal numbers. These numbers are grouped in 4s, giving 8 groups or blocks. The groups are written with a colon as a separator. Internet Protocol version 4, IPv4, is one of the core protocols of standards-based networking methods on the Internet. It was described in IETF publication RFC 791 in 1981, and it was the first version deployed for production in the ARPANET in 1983. It still routes most Internet traffic today despite the ongoing deployment of the successor protocol, IPv6. With IPv4, each address consists of 4 octets. Octet stands for 8-digit binary numbers. So an IPv4 address is 32 bits in total. So that means we can theoretically address 2 to the power of 32 devices with IPv4. So that means the address space of IPv4 is about 4.3 billion. Sounds like it's a big number, right? IPv4 is represented by the decimal equivalent of 4 octets separated by dots. The biggest number one can make with 8 binary digits is 2 to the power of 8 minus 1. That means 255. So each octet can be any number from 0 to 255. Now, also there are special meanings associated with 2 different ending numbers. In general, a last number of 0 stands for the network. Let's call that the base address. And a last number of 255 stands for all hosts on that network, called the broadcast address. Computers that are on the same local network share 3 of the 4 numbers. A computer can be on more than one network, so it can also have several names. So looking at an IP packet consisting of a header section and a data section, we'll see that the IPv4 packet header consists of 14 fields, and only the options field is, well, optional. Now, I'm not going to talk about each field one by one, but I'll give you a few short explanations of some of the more pertinent ones. The version field is always equal to 4. Why? IPv4. The Internet header length, IHL field, is the size of the header in words, where word is always going to be 32 bits. The total length is the entire packet size. In this case, it's in bytes. As you know, but to catch you up to speed, 1 byte is 8 bits. The minimum size is 20 bytes, so that's a header without data, and the maximum is 65,535 bytes. The flag is used to determine the fragmentation options. Bit 1 is DF, or don't fragment. If it's set, and I mean by that if this bit is a 1, and fragmentation is required to route the packet, then the packet is dropped. Bit 2 is MF, or more fragment. For fragmented packets, all fragments except the last have the MF flag set. Bit 0 is reserved for the future. TTL, or time to live, is to limit the lifetime of a packet. It's a hop count, basically. When the packet arrives at a router, the router decrements the TTL field by 1. Protocol field is the protocol used in the data portion of the IP packet. So that's going to be TCP, UDP, ICMP. Source address and destination address fields are the most important fields of an IP header. These fields are the IPv4 address of the sender of the packet and the IPv4 address of the receiver of the packet. Please note that this address may be changed in transit by a network address translation device. We'll talk about that later. This is how an IPv4 packet is seen on Wireshark. So it's a DNS query response. The fields we mentioned are seen pretty clearly. Version is 4. Header length is 5 words, which means no options field. Total length is 96 bytes. MF and DF flags are not set. And you can see the source and the destination addresses and all the rest. I know what you're thinking. You're really chomping at the bit to get to subnetting, but before we talk about it, it's better to learn the IP classes and the subnet masks first, right? Octets of the IP address are broken down to provide an addressing scheme that can accommodate large and small networks. So there are basically 5 different classes of networks, and they range from A to E. We're going to focus on classes A, B, and C, which provide unicast addresses for networks of 3 different network sizes. Class D is for multicast networking, and the Class E address range is reserved for future or experimental purposes. So given an IP address, its class can be determined from the 3 high-order bits, and by that I mean the 3 leftmost bits in the first octet. In a Class A address, the first octet is the network portion. So Class A has a major network address of 1.0.0.0 all the way through 127.255.255.255. The next 24 bits are for the network manager to divide into subnets and hosts as he or she sees fit. Class A addresses are used for networks that have more than 65,536 hosts. In a Class B address, the first 2 octets are the network portion. So Class B has a major network address of 128.0.0.0 all the way through 191.255.255.255. Octets 3 and 4, that means 16 bits, are for local subnets and hosts. Class B addresses are used for networks that have between 256 and 65,534 hosts. And finally, in a Class C address, the first 3 octets are the network portion. Class C has a major network address of 192.0.0.0 all the way through 223.255.255.255. Octet 4, 8 bits, is for local subnets and hosts. Perfect for networks with less than 254 hosts. So a network masks helps you know which portion of the address identifies a network and which portion of the address identifies the node. An IPv4 subnet mask consists of 32 bits, a sequence of 1 followed by a block of 0. The trailing block of zeros designates that part as being the host identifier. Class A, B, and C networks have default masks, also known as natural masks, and these masks are 255.0.0.0 for Class A, 255.255.0.0 for Class B, and 255.255.255.0 for Class C networks. So an IP address on a Class A network that has not been subnet would have an address mask pair similar to 131.107.1.2 being the address and 255.0.0.0 would be the subnet mask, right? Now, in order to see how the mask helps you identify the network and node parts of the address, convert the address and mask into binary numbers as seen on the slide. So once you have the address and the mask represented in binary, then identification of the network and the host ID is a lot easier. Any address bits which have corresponding mask bits set to 1 represent the network ID. Any address bits that have corresponding mask bits set to 0 represent the host ID. So in this example, the first part, 131.107, is the network part of the IP address, where the rest, 1.2, represents the host. All devices on this segment share the same network ID and the same subnet mask. Now you can customize the subnet mask to divide a network into many smaller portions. So here's a little brain tingler for you. The network ID may be expressed in classless interdomain routing, or CIDR, notation, written as the first address of a network, followed by a slash character, and ending with the bit length of the prefix. So in our example, 131.107.0.0/16 is the prefix of the IPv4 network starting at the given address, having 16 bits allocated for the network prefix and the remaining 16 bits reserved for host addressing. Your patience pays off. Subnetting allows you to create multiple logical networks that exist within a single class A, B, or C network. If you do not subnet, you are only able to use one network from your class A, B, or C network, which is, well, pretty unrealistic. So subnetting is the process of designating some high-order bits from the host part as part of the network prefix and adjusting the subnet mask appropriately. So this divides a network into smaller subnets. In other words, in order to subnet a network, extend the natural mask with some of the high-order bits from the host ID portion of the address in order to create a subnetwork ID. So I'll give you an example. Let's take a Class C network of 192.168.2.0, which has a natural mask of 255.255.255.0. You can create subnets by moving 2 bits from the host part to the network prefix. Now, the last octet of the network mask starts with 11. So this 8-bit corresponds to 192 in decimal form. Now the network ID is 26-bit. In CIDR notation, it's now a /26 subnetwork. You can find the network prefix by a bitwise AND operation between the IP address and the subnet mask. The number of subnetworks available and the number of possible hosts in a network may be readily calculated. In our example, 2 bits were borrowed to create subnetworks, thus creating 2 to the power of 2 possible subnets. You with me? So now let's calculate the maximum number of hosts for each subnet. In our example, 26 bits are used to define the network. The remaining bits after the subnet bits are used for addressing hosts within the subnet. So, the host part of the IP address is 6-bit. All zeros and the all ones values for the host ID are not allowed in a subnetwork, right? These 2 values are reserved for the network address and broadcast address, respectively. So the maximum number of hosts which can be addressed in these subnetworks is 2 to the power of 6 minus 2, which equals 62. Excellent. So as a result, the IP addresses of the devices in the subnetwork 192.168.2.128/26 will be between 192.168.2.129 and 192.168.2.190. So, as I mentioned before, the IPv4 address is a 32-bit number, which allows us to address maximum of 2 to the power of 32 devices in theory. That means there are fewer than 4.3 billion addresses available. See where I'm going with this? It's a problem because there are many more than 4 billion internet-connected devices in the world. Desktop and laptop computers, smartphones, smart TVs, smart cars, even smart fridges, smart ovens, the Internet of Things. It's the future, baby. This has led to a shortage of IPv4 addresses. So, my friend and fellow genius, what is the solution to the problem? I think the long-term solution is to switch to Internet Protocol version 6, IPv6. IPv6 has trillions of addresses, enough to give every computer in the world a unique IP address. We'll get into that detail very soon. But the most important effort to migrate the IPv4 shortage is using Network Address Translation, NAT, which allows a private network to use one public IP address, and that permits lots of private addresses in the private network. But wait a second, wait. Private network, NAT, what the heck are you talking about now? I thought you wanted to go to IPv6. Let me explain. Up to now, all the networks that we mentioned were assumed to be a public network, and all of the IP addresses were public IP addresses, right? In the Internet addressing architecture, a private network is a network that uses private IP address space. Wait. I'll try to explain an unknown with another one. But first, I should explain what the private IP address space is. Tell you what, let's take a break here, and I'll talk about the special use IP addresses, including the private IP address space. So the authorities, IETF and IANA, please don't ask. You can Google it if you really want to know who they are. But they've restricted from general use various reserved IP addresses for special purposes. So that means you cannot use any IP address in these reserved blocks as the public IP addresses of your devices. So here we have some of these reserved blocks. Now, these are the most important blocks for us to know, because pretty much anybody who's not familiar with the networking concept gets confused about the difference between public and private IP addresses. So these IP blocks are reserved for private networks. They're commonly used for home, office, and enterprise local area networks, or LANs. Private IP address spaces were originally defined in an effort to delay IPv4 address exhaustion, but they're also a feature of IPv6 where exhaustion is not an issue. Bear with me. Packets addresses in these ranges are not routable in the public internet because they are ignored by all public routers. Therefore, private hosts cannot directly communicate with public networks, but require Network Address Translation, or NAT, at a routing gateway for this purpose. But no worries, we'll talk about NAT coming up next. So without getting too deep, the only thing about the loopback is that 127.0.0.1 is the most common IPv4 address which is mapped to the local host. So let me give you an example. The IP address of your host machine is 172.16.99.222, and a web application is served in your host. Now, in that machine, you can use the web address hhp://127.0.0.1 to access the web app, as well as hhp://172.16.99.222. Both IP addresses point to the same machine, which is your host. Generally, an IP address that starts with 169 means that your computer wasn't able to obtain an IP address from your DHCP server. Usually that means that your router is wedged and needs to be rebooted, or that your Wi-Fi isn't working at all. So now let's have a look at the private IP address blocks closely. As I mentioned a few minutes ago, a private network is a network that uses private IP address space. Administrators of private networks can assign networks and subnets from the above ranges. If an administrator decides to use the IP range 192.168.0.0/16 and then decides to have a single subnetwork assigning 255.255.0.0 as a subnet mask, then he or she will have a subnet with a max of 65,536 devices. Make sense? Okay, I know there are a lot of terms and conditions, so let's just break it down with a real-world scenario. Although the standard for A and B class networks specify 8 and 16-bit masks respectively, it's common to assign non-standard masks for subnets, resulting in much more limited address spaces. Right? For example, using 10.xx.yy.0/24 results in 256 host company subnets, right? So this is done for scalability and, of course, security. Okay, so we're the system administrators in Company X and ready to build. We have decided to use 192.168.x.x as the private IP address space for our company. If we use the natural mask 255.255.0.0, that means we use the first 16 bits for network ID, and we'll have a single network. So in this case, we can address 65,536 devices in this network. Of course, the first IP and the last IP we're not allowed to use, so the number of IP addresses is actually 65,536 minus 2, you do the math, but in practice, for ease of use, it's pretty much used as the power of 2. So you can use an IP address in this network from 192.168.0.1 to 192.168.255.254. But we need to have different networks, one for the managers, one for the developers, one for the servers, etc. So, for the sake of our use and our sanity, let's use the next 8 bits for subnets. In this case, we have a subnet mask of 255.255.255.0, 8 bits for subnets, and 24 bits for the network ID in total, 8 bits left for addressing the devices under the subnets. So as a result, we can create 256 subnets and address 256 devices for each one. Now we have 256 address ranges for 256 subnetworks. So the table here shows a few examples of our potential subnetworks. The red colored blocks are added to the network ID as subnet identifiers. The rest of the 8 bits are used as the host IDs. In the 4-block decimal notation, the third block identifies the subnetwork and the last block identifies the host. So, breaking it down, it's much simpler now, isn't it? Excellent. Let's move on. So the private addressing scheme works really well for computers that only have to access resources inside the network, like workstations needing access to file servers and printers and so forth. Routers inside the private network can route traffic between private addresses with no trouble whatsoever. However, to access resources outside the network, like the internet for example, these computers need to have a public address so that responses to their requests return to them. Now this is where NAT comes into play. A workstation inside a private network makes a request to a computer on the internet. The switches or the routers within the network recognize that the request is not for a resource inside the network. So they send the request to the router, let's say the backbone router. Now the backbone router sees the request from the computer with the internal IP. It then makes the same request to the internet using its own public address and returns a response from the internet resource to the computer inside the private network. From the perspective of the resource on the internet, it's sending information to the address of the router. From the perspective of the workstation, it appears that the communication is directly with the site on the internet. So when NAT is used like this, all users inside the private network that access the internet have the same public IP address. So that means only one public address is needed for hundreds or even thousands of users. So let's have a look and see how it works. Here's a typical home network. There's a laptop, desktop PC, a smartphone, all connected to our home router. And the home router is, of course, connected to the internet. So when we register with our ISP, the Internet Service Provider, we get an IP address that is accessible throughout the internet, and that's pretty much assigned to that home router. We refer to it as real IP or public IP. Now suppose that the IP address 20.20.20.20 is assigned to our home router. Our devices inside the home network also have IP addresses, right? But in this case, they get private IP addresses, which are assigned by the home router and are not accessible from the internet. So as you can see here, the public IP addresses are red and the private IP addresses are green. So let's consider a connection request from the smartphone, which requests the homepage of abc.com. So to reach the page, the smartphone has to go through the home router. The packet has the source IP address and the source port address, as well as the destination IP address and the destination port. If it arrives at the web server with these values, it processes the request and tries to send the reply packet to the IP address 192.168.1.5. But that's unreachable for the web server because it's a private IP address. So, when the packet arrives at the home router, instead of sending the packet right over the internet, the home router changes the source IP address with its very own public IP address. It also creates a record in the NAT forwarding table. This table allows us to know which packets will be redirected to the smartphone when they come in. So moving right along, the packet travels over the internet and arrives at the web server. The web server creates a reply packet where the source IP address is itself and the destination IP address is the public IP address of the home router. When our home router receives a response, it looks at the NAT forwarding table and replaces the destination IP and the port according to the mapping inside the table. And finally, the smartphone receives the packet. Pretty cool, huh? IPv6 was developed by the Internet Engineering Task Force, IETF, I'm sure you looked it up, to deal with the long-anticipated problem of IPv4 address exhaustion. So IPv6 is intended to replace IPv4. IPv6 became a draft standard in December 1998 and became an Internet standard on the 14th of July, 2017. So instead of 32-bit addressing of IPv4, which provides approximately 4.3 billion addresses, IPv6 uses a 128-bit address. So that theoretically gives us 2 to the power of 128, or approximately 3.4 times 10 to the 38th addresses. Big number. You can check my math later, but stick with me for now. I mean, the actual number is slightly smaller, as multiple ranges are reserved for special use, or they're just completely excluded from use. But with a rough calculation, the total number of possible IPv6 addresses is more than 7.9 times 10 to the power of 28 times as many as IPv4. The two protocols, IPv4 and IPv6, are not designed to be interoperable, complicating the transition to IPv6. However, several IPv6 transition mechanisms have been devised to permit communication between IPv4 and IPv6 hosts. In addition to offering more addresses, IPv6 also implements features not present in IPv4. Simplified header. IPv6's header has been simplified by moving all unnecessary information and options, which are present in the IPv4 header, to the end of the IPv6 header. The IPv6 header is only twice as big as an IPv4 header because that IPv6 address is 4 times longer. End-to-end connectivity. Every system now has a unique IP address and can traverse through the Internet without using NAT or other translating components. After IPv6 is fully implemented, every host can directly reach other hosts on the Internet with some limitations involved, like a firewall, organization policies, and stuff like that. Auto configuration. IPv6 supports both stateful and stateless auto configuration mode of its host devices. This way, the absence of a DHCP server does not put a halt on inter-segment communication. Faster forwarding and routing. A simplified header puts all unnecessary information at the end of the header, like we saw earlier. The information contained in the first part of the header is adequate for a router to make its routing decisions, thus making them as quickly as looking at the mandatory header. IPsec. Initially, it was decided that IPv6 must have IPsec, making it more secure than IPv4. This feature has now been made optional. IPsec, Internet Protocol Security, is a framework of open standards for helping to ensure private, secure communications over Internet Protocol networks, IP networks, through the use of cryptographic security services. IPsec is an end-to-end security scheme operating in the network layer. While some other Internet security systems in widespread use, TLS and SSH, operate in the upper layers, IPsec can automatically secure applications at the IP layer. No broadcast. Though Ethernet and Token Ring are considered a broadcast network because they support broadcasting, IPv6 does not have broadcast support anymore. It uses multicast to communicate with multiple hosts. Mobility. IPv6 was designed keeping mobility in mind. This feature enables hosts, such as a mobile phone, to roam around in different geographical areas and remain connected with the same IP address. The mobility feature of IPv6 takes advantage of auto IP configuration and extension headers. Extensibility. One of the major advantages of the IPv6 header is that it is extensible, adding more information in the option part. IPv4 provides only 40 bytes for options, whereas options in IPv6 can be as much as the size of the IPv6 packet itself. What is the IPv6 packet, you ask? You came to the right place. An IPv6 packet is the smallest message entity exchanged via the Internet Protocol across an IPv6 network. But stay with me here. The packets consist of control information for addressing and routing, and a payload consisting of user data. The control information in IPv6 packets is subdivided into a mandatory fixed header and optional extension headers. The fixed header starts an IPv6 packet and has a size of 40 octets, which means 320 bits. Its format is shown in the slide. Version is constant 6. Payload length is the size of the payload in bytes, including any extension headers. Hop limit replaces the time to live field in the IPv4. Well, I think source address and destination address fields are fairly obvious. Extension headers carry optional Internet layer information and are placed between the fixed header and the upper layer protocol header. 128-bit IPv6 addresses are written using hexadecimal, as opposed to dotted decimal back in IPv4. Because a hexadecimal number uses 4 bits, This means that an IPv6 address consists of 32 hexadecimal numbers. These numbers are grouped in fours, giving 8 groups or blocks. The groups are written with a colon as a separator. An IPv6 address example is shown in the slide. So because of the length of the IPv6 addresses, various shortening techniques are employed. The main technique being to omit repetitive zeros, as shown in the example. So as I mentioned before, in IPv4, an address is split into two components, right? A network ID and a host ID. This was done initially using address classes and then later using subnet masking. In the unicast addressing of IPv6, it's done in the same way. The first step is to split the address into two parts. The address is split into two 64-bit segments. The top 64 bits is a network ID, and the lower 64 bits is the host ID. The most significant 64 bits are used for routing, and the least significant 64 bits identify the address of the interface or host. This block is derived from the actual physical or MAC address in practice. So if we look at the most significant 64 bits in more detail, we can see that it's split into two blocks of 48 and 16 bits. Now, the least significant 16 bits are used for subnets on internal networks and are controlled by a network administrator. The most significant 48 bits are used for the global network addresses and are used for routing over the Internet. Dynamic Host Configuration Protocol, DHCP. Now, it's a protocol used to provide automatic and central management for the distribution of IP addresses within a network. It's also used to configure the proper subnet mask, default gateway, and DNS server information on the device. In most homes and small businesses, the router acts as the DHCP server. In large networks, a single computer might act as a DHCP server. In short, the process goes like this. The device, the client, requests an IP address from a router, the host, after which the host assigns an available IP address to allow the client to communicate on the network. So let's look at some of the advantages of using DHCP. A computer or any other device that connects to a network, local or internet, must be properly configured to communicate on that network. Makes sense? Since DHCP allows that configuration to happen automatically, it's used in almost every device that connects to a network, including computers, switches, smartphones, gaming consoles, you name it. Now, because of this dynamic IP address assignment, there's less of a chance that two devices will have the same IP address, which is very easy to run into when using manually assigned static IP addresses. Using DHCP also makes a network much easier to manage. From an administrative point of view, every device on the network can get an IP address with nothing more than their default network settings, which is set up to obtain an address automatically. So that's easy, gives them nothing to call the help desk about. The only other alternative is to manually assign addresses to each and every device on the network. You're not getting paid enough to do that. So because these devices can get an IP address automatically, they can move freely from one network to another, given that they're all set up with DHCP, and receive an IP address automatically, which is super helpful with mobile devices. Now, as a cybersecurity expert, you should know one more thing about the DHCP mechanism. The first device which replies to a DHCP discover request decides the configuration of the client. There is not any mechanism to authenticate the DHCP server. Similarly, a DHCP server tries to reply to all the DHCP requests, and again, there is no authentication mechanism for the clients who request an IP. You get it? I think you do. What if a hacker replies before the real DHCP? Or what if a client sends a lot of DHCP discovery requests by changing the MAC address each time? So let's have a look to see how a DHCP mechanism works in detail. Once a device is turned on and connected to a network that has a DHCP server, it will send a request to the server called a DHCP discover request. After the discover packet reaches the DHCP server, the server attempts to hold on to an IP address that the device can use and then offers the client the address with a DHCP offer packet. Once the offer has been made for the chosen IP address, the device responds to the DHCP server with a DHCP request packet to accept it. After which, the server sends an ACK packet that's used to confirm that the device has that specific IP address and to define the amount of time that the device can use the address before getting a new one. If the server decides that the device cannot have the IP address, it will send a NAC. Let's see the DHCP server mechanism in Wireshark. So Wireshark is already embedded into Kali and it's ready to use. In addition, I'd also like to show you how to download and install it in a Windows system. So right now I'm in a Windows 8 system. Open the internet browser and search for Wireshark for Windows, using those as the keywords. First link is the download page of wireshark.org. So let's click it. My Windows is 64-bit, so I'll download the 64-bit, which is the latest stable version. Click it and save the installer. Now it takes less than a minute unless your connection is a mess. You might want to look into that. Just kidding. Click to run it. The setup wizard opens. Okay, so simply it's a next, finish installation. No need to change anything. Wait until the installation finishes. Okay, so check this to run Wireshark now and click Finish. And welcome to the Wireshark and Windows interface. So now I will show you the DHCP mechanism in Wireshark. So let's run Wireshark, and you can see that it's listing the packets received by ETH0. So to demonstrate the DHCP mechanism, we need to ask for an IP address over at the DHCP server. From the bottom right corner, right-click to the network icon and select Open Network and Sharing Center. Click Ethernet 0 and then Properties. You'll have to scroll down a little bit and double-click IP version 4. And as you see here, the IP address is manually set for my Windows 8. So to start a DHCP request, I'll choose Obtain an IP address and DNS server address automatically. Those are my options. Now before I click OK, I'll go to Wireshark and restart capturing by clicking the green button on the toolbar. So now Wireshark Windows will be cleaned. Continue without saving. So now go to the network status window and click OK. And we can close all the networking windows. So Wireshark captured the packets. Well, it's still capturing, but let's go to the top of the list to find the DHCP packets. So here the DHCP Discover packet is right here at the top of the list. When we look at the ports in the UDP header, we see that the port 68 is used to send DHCP Discover packets. So let's go back to the filter box and type UDP port equals 68. And now we have the DHCP packets only. So the first packet is DHCP Discover. And as I mentioned before, it's broadcast. Source IP is all zeros because we don't have an IP address at the moment. Destination IP is all ones, 255.255.255.255 because it's a broadcast packet. And right here is Bootstrap Protocol, which is an application layer protocol used by DHCP mechanisms. The second packet is a DHCP offer packet sent by the DHCP server, 172.16.99.254, to the Windows system. Destination IP is 172.16.99.233, which is offered to the DHCP server. So in here, the destination MAC address is important. That's what's going to be targeted according to the MAC address. So as you see, the destination MAC address of the DHCP offer packet is the same as the source MAC address of the DHCP discover packet. Now the third packet is the DHCP request sent by the Windows system. It's still a broadcast packet and the source IP is still all zeros. The message is request and the requested IP address is an option 50. So if you expand it, you see the requested IP address. And it's the same as the offered IP address 172.16.99.223. The last packet is DHCP ACK, sent by the DHCP server to the Windows system. This packet completes the DHCP mechanism successfully. So from now on, the IP address of our Windows system is 172.16.99.223. Internet Control Message Protocol, ICMP, is an error reporting protocol that network devices like routers use to generate error messages to the source IP address when network problems prevent delivery of IP packets. ICMP messages are sent in several situations. For example, when a datagram cannot reach its destination, when the gateway does not have the buffering capacity to forward a datagram, and when the gateway can direct the host to send traffic on a shorter route. The Internet Protocol is not designed to be absolutely reliable. I'll explain why. Hold on. The purpose of these control messages is to provide feedback about problems in the communication environment, not to make IP reliable. There's still no guarantees that a datagram will be delivered or a control message will be returned. Some datagrams may still be undelivered without any report of their loss. The higher-level protocols that use IP must implement their own reliability procedures if reliable communication is required. So the ICMP header starts after the IPv4 header. All ICMP packets have an 8-byte header and variable-size data section. The first 4 bytes of the header have a fixed format, while the last 4 bytes depend on the type and code of that ICMP packet. ICMP type and code in the header identifies the control message. Some of the ICMP control messages are shown in this slide. So ping is the most well-known application of the ICMP. It operates by sending ICMP echo request packets to the target host and then waiting for an ICMP echo reply. Some routers and firewalls are configured to not pass ICMP echo requests or echo reply requests. Attackers sometimes try to map out remote networks by pinging all the possible addresses and collecting replies. So blocking this type of traffic at the perimeter is fairly common. Just because you do not receive a reply to a ping does not necessarily mean that the host is not available. Traceroute is a computer network diagnostic tool for displaying the route or path of packets through the internet between your computer and a specified destination computer. It also measures the amount of time each hop took. When you run the utility, it initiates the sending of a packet, including in the packet a TTL, a time-to-live value, which is also known as a hop limit. As the packet passes through a router, the TTL is decremented until when the TTL reaches 0, the packet is destroyed and an ICMP time exceeded message is returned. Traceroute works by setting the TTL for a packet to 1, sending it towards the requested destination host, and listening for the reply. When the initiation machine receives a time-exceeded response, it examines the packet to determine where the packet came from. So this identifies the machine 1 hop away. Then the tracing machine generates a new packet with TTL 2 and uses that response to determine the machine 2 hops away. and so on. The command traceroute is available on many modern operating systems. On Unix-like systems such as FreeBSD, macOS, and Linux, it's available as a command line tool. On Unix-like systems, traceroute sends, by default, a sequence of UDP packets. Traceroute is also graphically accessible in macOS within the Network Utility Suite. In Microsoft Windows, it's named Tracert. In Windows, traceroute sends ICMP echo requests instead of UDP packets. For IPv6, the tool sometimes has a name traceroute 6 or tracert 6. Let's look how the traceroute command operates in our host machine and virtual machines as well. So I'm on my host machine. This is Mac OS. And I'll open a terminal screen, Command Space to open the Spotlight search bar, and type terminal. Start the terminal app, and now I'm on a terminal screen. Traceroute is the command I'll use. So if you run it with no parameter, you get a brief help about the usage of the command. So now let's run the command with a target host. We timed out in the first hop. And in the second one as well. Well, it happens, no worries. And yes, here are the other hops. This is the path that the packets follow from my host machine to the target web server. In Mac OS, you can also trace the packets with a graphical UI, which I mentioned before. So go to the Network Utility tool, press Command and Spacebar once more to open Spotlight, and type Network Utility and find it and open it. There's a Traceroute tab in the Network Utility window. Just type the target host and click the Trace button. Let's see how it all works in Kali. So now I'm in Kali and I have a terminal screen open. Type traceroute and hit enter. So you'll see the help for this particular command, and it's a bit more detailed than the one in macOS. So now I want to show you the network configuration of my Kali. Go to Kali settings, click Network Adapter, and as you see, we run Kali in NAT mode, where the host machine, Mac, provides network address resolution, we'll talk about that soon, for all network traffic, and Kali shares the IP address of the host. Now I want to test the network connection first. So I'll ping the Google DNS 8.8.8.8, and right, that's no problem at all. You can use Control-C keys to end the ping command. Just don't use Control-L. Okay, now I'll run the traceroute with the target host in Kali. The first hop is a gateway prepared by VMware for my virtual machines. And as you can see, all the other hops are blocked. We cannot trace packets from the VM in NAT mode. So let's have a look at the traceroute command options once more. Here there's an option, uppercase T, which sends TCP SYN packets. Now I'd like to try the command once more with this option. Okay, so we have the first and the last hop this time. So now I want to show you the command in a Windows system. Here is my up-to-date Windows 8 system. It has an IP. Check the connection, ping, and yes, the network is running. Good, just where we want it. Let's look at the network details first. From the Network and Sharing Center, click Ethernet 0, and then the Details button, and here are the details. Default gateway is 99.2, DHCP is 99.254, as you know. These are the devices prepared by VMware for our NAT network. So now I go to the settings of the VMware Fusion. In Network Adapter, we confirm that the VM is in network mode. Now I'm in the command prompt. As I mentioned, the command is tracert in Microsoft systems. So write down the target host and press enter. So the first hop is, again, the gateway. And just like in Kali, since this VM is also in that mode, the requests for other hops are timed out. So while the command is running, I'd like to show you the command help. So just type tracert and hit enter. So we didn't enter the host this time, and here's a usage of the tracert command. Trace completed, and there is no result given, as expected, because we're in that mode. I know you knew that, but I just wanted to make sure. So now I'm going to run my Windows VM in bridge mode and try the command once more. And once again, click the hardware settings icon on the menu bar of VMware Fusion and select Network Adapter. So I'm using Wi-Fi to connect to the internet right now, so I choose Wi-Fi under the bridged networking section. Now this is the IP address assigned by the DHCP, and the subnet mask of the network, again, is set by DHCP. So we'll see how the DHCP works. Just stay with me here. So as you see in the Network and Sharing Center window, the active network disappeared as soon as I changed the network adapter of the VM. In a second, the new network is activated. Click Ethernet 0 and look at that, the Details button. So click on that to see the network settings, and those are the new ones. So now we're in the 192.168.12.x IP block. And we have a different DHCP and gateway run by the network admins of my office building. So let's go back to the command prompt and trace the route of the packets once more. So first I want to check the network, as I always do. So I'll ping the Google DNS, and yes, we have the internet connection. So now is the time to trace the route. The first request is timed out. Remember, the results of my host machine, right? The second request timed out as well. And here are the other hops. We now have the results. So now we're in the fourth layer of the OSI reference model, the transport layer. Welcome to the layer of TCP. The transport layer is the level at which system reliability and quality are ensured. The basic function of the transport layer is to accept data from the layer above, split it up into smaller units, pass these data units to the network layer, and ensure that all the pieces arrive correctly at the other end. Okay, so now let's look at the functions of the transport layer in detail. Service point addressing. Transport layer header includes service point address, which is the port address. This layer gets the message to the correct process on the computer, unlike network layer, which gets each packet to the correct computer. Segmentation and reassembling. A message is divided into segments. Now each segment contains a sequence number, which enables this layer to reassemble the message. The message is reassembled correctly upon arrival at the destination and replaces packets which were lost in transmission. Connection control. It includes two types. Connectionless transport layer. Each segment is considered as an independent packet and delivered to the transport layer at the destination machine. Connection-oriented transport layer. Before delivering packets, connection is made with the transport layer at the destination machine. Flow control. In this layer, flow control is performed end-to-end. The rate of data transmission between two nodes must sometimes be managed to prevent a fast sender from transmitting more data than can be supported by the receiving data buffer, causing a buffer overrun, and we don't want that. Error control. Error control is performed end-to-end in this layer to ensure that the complete message arrives at the receiving transport layer without any error. Error correction is done through retransmission. On the Internet, TCP and UDP provide the services for most applications. Coming up next, we'll look at all the other details of the transport layer under TCP and UDP topics. The Transmission Control Protocol, TCP, provides a communication service at an intermediate level between an application program and the Internet protocol. It provides host-to-host connectivity at the transport layer of the Internet model. TCP works with the Internet Protocol, IP, which defines how computers send packets of data to each other. Together, TCP and IP are basic rules defining the Internet. TCP is a connection-oriented protocol, which means a connection is established and maintained until the application programs at each end have finished exchanging messages. It determines how to fragment application data into packets that networks can deliver, sends packets to and accepts packets from the network layer, manages flow control, and, because it is meant to provide error-free data transmission, handles retransmission of dropped or garbled packets, as well as acknowledgement of all packets that arrive. Let's see the connection-oriented error-free communication of TCP in an example. When a web server sends an HTML file to a client, it uses the HTTP protocol to do so. The HTTP program layer asks the TCP layer to set up the connection and send the file. The TCP stack divides the file into packets, numbers them, and then forwards them individually to the IP layer for delivery. Although each packet in the transmission will have the same source and destination IP addresses, packets may be sent along multiple routes. The TCP program layer in the client computer waits until all of the packets have arrived, then acknowledges those it receives and asks for the retransmission on any it does not, based on missing packet numbers. Then assembles them into a file and delivers the file to the receiving application. The TCP three-way handshake is the method used by TCP to set up a connection. TCP's three-way handshaking technique is often referred to as SYN, SYNAC, ACK, because there are three messages transmitted by TCP to negotiate and start a TCP session between two computers. This three-way handshake process is also designed so that both ends can initiate and negotiate separate TCP socket connections at the same time. That means the connection is full duplex. Oh, you know what? We have to take a break at this point and talk about TCP flags. There are 1-bit flags in TCP headers, which are called TCP flags. TCP flags are used within TCP packet transfers to indicate a particular connection state or provide additional information. Ignoring ECE, CWR, and NS flags for now, there are basically 6 TCP flags. The SYN, or synchronization flag, is used as a first step in establishing a three-way handshake between two hosts. Only the first packet from both the sender and the receiver should have this flag set. The ACK flag, which stands for acknowledgement, is used to acknowledge the successful receipt of a packet. The RIST flag, which stands for reset, gets sent from receiver to the sender when a packet is sent to a particular host that was not expecting it. The FIN flag, which stands for finished, means there is no more data from the sender. Therefore, it is used in the last packet sent from the sender. The PSH flag, which stands for push, is somewhat similar to the URG flag and tells the receiver to process these packets as they are received instead of buffering them. The URG flag is used to notify the receiver to process the urgent packets before processing all other packets. So every legitimate TCP connection begins with a TCP three-way handshake, which is used to exchange sequence numbers so that lost packets can be retransmitted and packets can be placed in the proper order. If machine A wants to initiate a connection to machine B, it will start by sending a TCP packet with a SYN control bit set. This packet will include an initial sequence number, which I'll call here ISNA because it comes from machine A, which is 32 bits long and typically generated in a pseudo-random fashion by the TCP software on machine A. The ACK number, another 32 bits in the TCP header, is typically set to 0 because it is ignored in this initial SYN. Some operating system variants may make this ACK number non-zero, but either way, it's ignored by the destination machine. So if the destination port is open, that is, there is something listening on that port, it must respond with a SYN ACK packet back, a packet that has both the SYN and ACK control bits set at the same time. This packet will have a sequence number of ISNB, a pseudo-random number assigned by machine B for this connection. The SYN ACK packet will have an acknowledgement number of ISNA plus 1, indicating that machine B has acknowledged the SYN packet from machine A. To complete the three-way handshake, machine A responds with an ACK packet which has a sequence number of ISNA plus 1. It's the next packet, so the sequence number has to change from the value in the original SYN packet. The acknowledgement number field is set to ISNB plus 1, thereby acknowledging the SYN ACK packet, right? So we have now exchanged sequence numbers. All packets going from A to B will have increasing sequence numbers starting at ISNA plus 1, going up by a value of 1 for each byte of data transmitted in the payloads of A to B packets. Likewise, all responses back from B will have sequence numbers starting at ISNB plus 1 and going up for each byte of data from B to A. In essence, we have two streams of sequence numbers in this series of packets, one from A to B, originally based on ISNA, and the other from B to A, originally based on ISNB. Perfect. A TCP segment consists of a segment header and a data section. The TCP header contains 10 mandatory fields and an optional extension field. The optional field is the options field, which is the last field seen on the slide. The TCP header includes a source port and destination port, each 16 bits in length. The source port is the port on the originating machine that emitted the packet. The destination port indicates the port on the target machine the packet should be delivered to. The sequence number and an acknowledgement number allows TCP to track a series of packets to make sure they arrive reliably and pretty much in order. No, absolutely in order. If a packet is lost, TCP will retransmit it. If packets arrive out of order, TCP will adjust them to make sure that they are delivered to the destination services in the proper order. Data offset specifies the size of the TCP header in 32-bit words. The minimum size header is 5 words, and the maximum is 15 words. There is also TCP control bit space, also known as flags, which are incredibly important for tracking the state of a given TCP connection. As you know, we talked about them a few minutes ago. Of course, if you didn't take a break, it was a few minutes ago. But whatever you do, just don't spill on the keyboard. Now, TCP senders use a number called window size, which is in bytes by default, to regulate how much data they send to a receiver before requiring an acknowledgement in return. So if the window size becomes too small, network data transfer will be unnecessarily slow, while if the window size becomes too large, the network link can become saturated or the receiver may not be able to process incoming data quickly enough. also resulting in slow performance. Windowing algorithms built into the protocol dynamically calculate size values and use this field of the TCP headers to coordinate changes between senders and receivers. A full duplex communication is established. UDP is another protocol of transport layer, layer 4, used primarily for establishing low latency and loss-tolerating connections between applications on the Internet. TCP has emerged as the dominant protocol used for the bulk of Internet connectivity owing to its services for breaking large data sets into individual packets, checking for and resending lost packets, and reassembling packets into the correct sequence. But these additional services come at a cost in terms of additional data overhead and delays called latency. In contrast, UDP just sends the packets, which means that it has a much lower bandwidth overhead and latency. But packets can be lost or received out of order as a result, owing to the different paths individual packets traverse between sender and receiver. So UDP uses a simple connectionless communication model with a minimum of protocol mechanism. It has no handshaking dialogues and thus exposes the user's program to any unreliability of the underlying network. There is no guarantee of delivery, ordering, or duplicate protection. UDP is suitable for purposes where error checking and correction are either not necessary or are performed in the application. UDP is an ideal protocol for network applications in which perceived latency is critical, such as gaming, voice, and video communications, which can suffer some data loss without adversely affecting perceived quality. In addition, since it's transaction-oriented, suitable for simple query response protocols such as the domain name system or the network time protocol. The UDP header is pretty simple. It consists of 4 fields, each of which is 2 bytes, 16 bits. The use of the fields checksum and source port is optional in IPv4. Are you surprised to hear that the source port is optional? But don't be, because, as you know, a UDP packet does not expect to get a reply in general. And again, since UDP doesn't care about the errors, the checksum field is, again, optional. Source port identifies the sender's port, and the destination port identifies the receiver's port as well. And the length field specifies the length of the UDP header and data in bytes. So now's a good time to compare the two protocols, UDP and TCP, as a brief summary. Most services on the Internet use either TCP or UDP, which are carried end-to-end across the network using IP, either IPv4 or IPv6. The Transmission Control Protocol, TCP, and User Datagram Protocol, UDP, are very different. TCP is a connection-oriented protocol which tries to ensure reliable, in-order delivery of packets. If packets are lost, TCP automatically retransmits them. If they arrive out of order, TCP will resequence them before handing them up to an application. UDP is connectionless. The UDP software makes no attempt to associate streams of packets together. So as far as UDP is concerned, each packet is completely independent, unrelated to other packets. No attempt is made by UDP for retransmission or resequencing. If a packet is lost via UDP, it's up to the higher layer application to resend it. The often used analogy to explain the domain name system is that it serves as the phone book for the Internet by translating human-friendly computer host names into IP addresses. Simply, DNS is a directory of names that match with IP addresses. As you may know, each device connected to the Internet has a unique IP address which other machines use to find the device. DNS servers eliminate the need for humans to memorize IP addresses, such as 212.80.75.134. Think about the websites you visit every day, Google and YouTube, Facebook, Twitter, etc. Without DNS, we would have to reach these sites by using their IP addresses instead of their names. I think remembering the names is so much easier than remembering the strange numbers. But it's still possible to reach the computer with that strange number string as well. Now, DNS deserves to have far more time spent on it. It could be a whole course in and of itself. But I just want to explain it simply without going too deep. So when you enter the URL, such as www.google.com, into the web browser, the request is not directly sent to the Google servers. Instead, the request goes to the DNS server that uses a lookup table to determine the IP address of the website that is being requested. Then it forwards this information to the proper servers and returns the information requested to your specific browser. DNS server is a computer server which contains a database of public IP addresses and their associated host names. It translates those common names to IP addresses as requested. DNS servers run special software and communicate with each other using special protocols. DNS is a client-server network communication system. DNS clients send their requests to and receive the responses from DNS servers. The requests containing the name and resulting in an IP address being returned from the server are called forward DNS lookups. The requests containing IP addresses and resulting in the names are called the reverse DNS lookups. The DNS directory that matches name to number isn't located all in one place. Pretty much like the internet itself, the directory is distributed around the world, stored on domain name servers that all communicate with each other on a very regular basis to provide updates as well as redundancies. With more than 332 million domain names listed by the end of 2017, a single directory would be very large indeed. So when you type mail.google.com into your browser sends a query over the internet to find the website. It's a query seeking to match the domain name with its corresponding IP address. So let's follow the path of this question over the internet infrastructure. The first server your query interacts with is the DNS resolver, which can be operated by your ISP, Internet Service Provider. A resolver is basically responsible for initiating and sequencing the queries that ultimately lead to a full resolution. Domain name resolvers determine the domain name servers responsible for the domain name in question by a sequence of queries, starting with the rightmost, in other words, top-level domain label. Assuming the resolver has no cached records to accelerate the process, which is the worst-case scenario, the resolution process starts with a query to one of the root servers. The root servers are running all over the world, and each one knows DNS information about top-level domains, or TLD, such as .com. So to begin answering your query, the resolver asks a root server for DNS information about .com. So there are 13 sets of root servers in more than 300 locations around the world. Each TLD DNS name server stores the address information for second-level domains within the top-level domain, .com in our example. The second-level domain is google.com. When your query reaches the TLD server answers with the IP address of the domain's name server, which will provide the next piece of the puzzle. So this is the final step of address resolution. The recursive resolver sends the query to the domain's name server. This DNS server knows the IP address for the full domain, mail.google.com, and that answer is returned to the recursive resolver. Now that the recursive resolver knows the IP address for the domain name in your query, the recursive resolver tells the browser what the IP address is. So finally, your browser can send a request to the website to retrieve the website's content, using the IP address it just learned. This whole process might seem, well, complicated. It certainly sounds it to talk it out, but really takes very little time at all. Hypertext Transfer Protocol, HTTP, is an application protocol. Hypertext is basically structured text that uses logical links between nodes containing text. And HTTP is the protocol to exchange or transfer hypertext. So HTTP is a stateless protocol. That means no information is retained by either sender or receiver. It functions as a request-response protocol in the client-server computing model. A web browser, for example, may be the client, and an application running on a computer that's hosting a website may be the server. The client submits an HTTP request message to the server. The server, which provides resources such as HTML files and other content, returns a message to the client. The response contains completion status information about the request and may also contain requested content in its message body. So the most used HTTP request is GET. A GET request is designed to request server resources. With this type of request, the parameters are sent to the server inside the URL. A POST request is designed to request server resources as well as a GET request. Unlike a GET request, parameters are sent to the server inside the body of the request instead of the URL. Well, it's still possible to send the parameters inside the URL, but if you use a POST request, it's better to send parameters inside the body than inside the URL. So what's the advantage of sending parameters inside the body instead of the URL? Almost always, the traffic between the server and the client is logged on the server side. Such log files usually contain the URL. If you send the parameters in the URL, they are saved as clear text in your log files. So anyone who can see the log files can also see your sensitive parameters. You should use POST requests to send sensitive data. But please note that it's not enough for the privacy of the traffic, because any man in the middle who listens to the network will see the parameters even though they are inside the body of the request message. So you should encrypt your traffic, always. Now, the server, which provides resources such as HTML files and other content, returns a response message to the client. The response contains completion status information about the request and may also contain requested content in its message body. So every response has a 3-digit response status code, such as 200 OK, 302 found, etc. Now, HTTPS consists of communication over HTTP within a connection encrypted by TLS, Transport Layer Security, or its predecessor, SSL, the Secure Sockets Layer. The main motivation for HTTPS is authentication of the visited website and protection of the privacy and integrity of the exchanged data. So let's see how a typical encrypted connection between the server and the client is established. The client sends the information that the server needs to communicate with the client using SSL. This information contains the client's SSL version number, cipher settings, and session-specific data. The server then sends the information that the client needs to communicate with the server over SSL. The server also sends its own certificate. The client uses the information sent by the server to authenticate the server. So using all data generated in the handshake thus far, the client creates the pre-master secret for the session, encrypts it with the server's public key, and then sends the encrypted pre-master secret to the server. The server uses its private key to decrypt the pre-master secret, and both the client and the server perform a series of steps to generate the master secret. Then, they use the master secret to generate the session keys, which are symmetric keys used to encrypt and decrypt information exchanged during the SSL session and to verify its integrity. The client sends a separate message indicating that the client portion of the handshake is finished, and the server sends a separate message indicating that the server portion of the handshake is finished. Hello, and welcome to the Network and Layer 2 Attacks and Countermeasures course. Now, throughout the course, we're going to learn the following topics. First, we'll prepare the lab environment for hands-on experiments. Second, we'll learn how to sniff the network and gather information from the network. We're going to use some tools such as TCP dump and Wireshark. Then, we'll see some attacks and techniques to expand the sniffing service. MAC address table overflow attack, also known as MAC flooding. ARP cache poisoning attack, also known as ARP spoof. DHCP starvation attack and DHCP spoof. And VLAN hopping techniques. The next topic is what else can be done on network devices in penetration tests. Gathering information, cracking passwords of the communication channels, compromising SNMP, etc. Finally, we'll check the configurations of the network devices, the password creation methods, identity management, access control lists, port security, and the list goes on. You with me? You can use any virtualization platform such as Oracle VirtualBox or VMware Player. While using virtual environments, the virtual machines should be on the same network to see each other. Now, we're going to use virtual machines in NAT mode. If you're using VirtualBox because of its architecture, you should create a NAT network. If you use a virtual machine in NAT mode without configuring any NAT network, a network is created for that virtual machine, and it doesn't see other virtual machines even if they are in NAT mode. If you're using one of the VMware tools such as VMware Player, Fusion, or Workstation, using NAT mode for network interfaces will be enough for the virtual machines to see each other. Oh, and I should probably tell you that since there are a lot of vulnerabilities in it, do not use the virtual machines in bridge mode, which are intentionally vulnerable, such as Metasploitable or OWASP broken web applications. If you use them in bridge mode, they will be accessible in the network where your host machine is. Someone in that network might hack the vulnerable virtual machines and try to access the host machine, which means your computer. Now, if you would like to use virtual machines in host-only network mode, please just learn how the virtualization platform works in that mode first. As the target systems, we will use a few devices. One of the target devices will be OWASP, Broken Web Applications, or BWA. Now, Broken Web Applications is a virtual machine that hosts a lot of applications prepared for training purposes. These apps are intentionally have a lot of vulnerabilities and can also be accessed from a main page. The virtual machine is prepared by OWASP, Open Web Application Security Project, which is one of the most important communities around in the application security market. So I'm now on my host machine. It's a MacBook. Open a web browser and Google for OWASP, Broken Web Applications. Those are my keywords. The first website is the official website of the Broken Web Applications Project, hosted under the owasp.org domain. So let's click it. Now, this is the web page of Broken Web Applications. I'll call it BWA from now on. So there are some explanations about this project here, so you can read them if you want. But over here on the right-hand side, we have download the latest release. So click on that. Now, we're directed to the SoundForge website. So these are the side effects of GDPR. We'll have to see a lot more approval pages like this one. Okay, so these are all the releases of the project, and the latest version is right here at the top. So click on it, and now I have 3 different options to download: .ova file, a .zip file, and a .7z file. Now, an OVA file is a virtual appliance used by virtualization applications such as VMware and Oracle VirtualBox. It's a package that contains files used to describe a virtual machine. Zip and 7Z are the archive files, and they contain the exact same VM. So you can download any one of them where the 7Z file is smaller. Okay, so I want to download the 7Z file, which is the most popular one already. So click on the link and download will start in just a couple of seconds. There we go. And the download's finished. So now I have an OWASP BWA archive file. So I'll open it with an unarchiver and double click, and here are the files inside the archive. So I already have the VM, so I won't extract it again. When you extract it, you will have a folder like this. So go to the folder, and here are the files of the virtual machine. If you run the .vmx file, double click, the VM starts. If it's the first run, it asks you whether you moved it or copied it. Select Copied and continue. Right, so while the VM is starting, let's have a look at its settings by clicking this button. Click here to look at the memory. 1024 megabytes of RAM is recommended. Click Show All to turn back to the settings. Network settings are here. So my VM is in an unrecognized network mode. Don't pay any attention to that. Your VM is probably in NAT mode by default. I choose Share with my Mac so that I can use the VM in NAT mode. So now the VM has started and we're ready to log in. It has a root user with the password OWASP BWA by default. I haven't changed it before, so I'll log into the VM by using this credential. If configured, check if it has got an IP address, and there it is, so yes it has. Now, ping a system on the internet. Google DNS, for example, 8.8.8.8, and we'll receive the replies. So it seems everything's fine, and we're ready to use OWASP Broken Web Applications VM. Okay, guys, so in all of my courses, I intend for the participants that they easily make hands-on practice on their own computers. So to achieve this purpose, in network layer attacks, we're going to use a network emulator. With its famous name, GNS3, or Graphical Network Simulator 3, it's a network software emulator. It allows the combination of virtual and real devices used to simulate complex networks. So we'll see how to set one up and use GNS3 throughout the course. However, I do have to say that it's not an easy-to-use tool. I'll try to keep it as simple as possible for you, but just stay with me and you'll get it too. Anyway, if you don't want to deal with the GNS3, you can skip this section, even though I wouldn't recommend it. You'd still be able to make the most of the course, but like I'm saying, stick with me and I think you'll get it too. So now let's download and install the GNS3 tool on our host machines. Since my host system is a MacBook, I'll show the installation in macOS. The installation steps are similar in other operating systems, so don't worry, you won't face any difficulties. If you do, just let me know and we will go through this step by step. All right, so open a browser in your host machine and go to gn3.com. Click Free Download. An account is required to download GNS3 software, so create an account. You can use your genuine email address, it's no problem. Since I already have an account, I'll use a Yop mail address at this time. So assign a password, select a country. I'll use it for training purposes. Okay, create account and continue. Select the appropriate install file to download. My host machine is a Mac, so I'll choose Mac. Download finishes in a couple of seconds. I mean, if you've got the same bandwidth as I do. Now, select the installation file and double-click to start the installation. I'll just drag the icon and drop it onto the Applications folder, and that's about it. So I'm ready to use GNS3. Now, I can go to the Applications window and click GNS3 to start it up. Okay, so in Mac, the files from a developer which is not identified by Apple are not allowed to run. To get rid of this, I'll just go to System Preferences, select Security and Privacy, and you'll see the GNS3.app was blocked message. Click the padlock icon at the bottom left corner, enter your password to allow the changes, and click Open Anyway. Right there next to the GNS3 was blocked message. Click Open, and GNS3 starts. So let's create our first project in GNS3. Now at this point we have a choice to make, so whether we run GNS3 on the local server or within a virtual machine. Because the primary reason for using GNS3 is simulating a network with switches and routers, all we have to do is select the Run Only Legacy iOS on my computer. That's the option which is not selected by default. So we can leave this page with the rest of the default values. It asks for the root permission for uBridge to interact with a network interface. So click Yes to allow and enter the admin password. Local server is started up and GNS3 connected to it successfully. So click Next. Finally, we have the summary of the project settings, so click Finish to end the project setup. So as soon as you click Finish, the new appliance template window appears. So at this point, we're going to add an iOS router using a real iOS image. So select the option and click OK. So I'm assuming that you're a first-time user of GNS3, and as such, you need to be aware that in order to use this application software, at the minimum, you need to download one more piece of software. So we already downloaded and installed the GNS3 software itself, which actually comes bundled with a whole bunch of other stuff, which isn't really needed. And then you're also going to download at least one Cisco iOS software image. I would suggest that you would get hold of software images that support either the 3725 series router or the 3745 series router. If you can get hold of these, that'll be the best. So if you don't know anything about Cisco routers at all, you're just looking for some advice on which particular one to choose for your iOS image. I would select a 3725 or a 3745 image. If you get software images for one that's 3700 series of routers that comes along with like a switching module, you don't have to download anything else. There's nothing that you have to do. But basically, you can turn on a switch that operates within or inside of that router, and then I can do the switching and routing. Most of the other platforms do not support that. So in my particular case, I'm going to use a 3725 image. And now I get to the point when we get to choose what iOS image we want to import into GNS3. And here's where you get to browse for wherever you've downloaded the Cisco IS software to. I'm going to use a 3725 image, which I've already downloaded. If you don't have it already, please search for the keywords such as Cisco iOS 3725 image download, and you'll find an image and then download it for yourself. I'd love to show it to you, but I don't want to mess with legal issues. It's not so hard, and I'm sure that you can easily find one. Now, click Browse to select the iOS image. So let me find my image. Here it is. Select it and click Open. And yes, I would like to decompress the image. So click Next. Give a name, make it up as whatever you want. I'm going to choose C3725. That's pretty good for me. So now before I leave the screen, there's also a little box here that says this is an ether switch router. So you can just have every router in your topology as an ether switch. I'm going to leave that unchecked for now. We'll create a legacy router right now. So make the default RAM 256 megabytes and then click Next. So here's where I get to select what modules or port adapters I want in my chassis. It comes with a fast Ethernet slot already on it. And now I've selected in another slot so I can put another fast Ethernet card, and then I'll put another fast Ethernet card. Why not? So as I go forward, I've got some WIC slots available. Once again, these slots are available in the 3725. Depending upon that software that you're using, you might not have all of these available to you. So I'm going to put some serial interfaces in these slots. So I'm going to have tons of interfaces in every single one of my routers to give me lots of flexibility in the types of topologies that I want to design. Don't worry, we can change all these settings after the setup as well. So now click Next. Now, I don't want to waste time for the idle PC. We can simply say that it's used to make the CPU usage much more effective. So just click Idle PC Finder and let GNS3 find one for you. And now we can hit Finish. And a router is available to us. Now we can use it in our virtual topology. All right, so here are the preferences of GNS3. The router is added under the Dynamips iOS Routers menu. You can see the menu on the tree at the left-hand side of the window, so click OK to close the Preferences window. Now is the time to name our first GNS3 project. As you can see here, the project location changes as well when you change the project name, so click OK once you finish naming it. And this is your main GNS3 window. So now let's create another iOS router template and make it an ether switch router this time around. Now from the GNS3 main menu, select Preferences. From the left-hand side menu, select iOS routers under the Dynamips submenu and click New. We can use our existing image right now, so click Next. And I'd like to turn this router into a switch by selecting the Ether switch box. Let's go ahead and change the RAM to 256 megabytes. So now you can see it automatically populates one of those slots with a 16-port switch module, and if you want, you can just leave it that way if the only thing that you're planning in the router is for a 16-port Ethernet switch. But what I want to do is add more flexibility, so I'm going to add some more slots, just like the previous scenario. Let the app find an idle PC. And then click Finish. Now we have two different router templates. The first one is a classic router, and the second one is an ether switch router. Now you can click Edit to remove or add new slots, change a name, change a RAM size, whatever you want to do to customize it. Great, so now let's get to know GNS3 closely. It's closed at the moment, so I'll go to the Applications menu and run GNS3 by clicking on its icon. The project window appears at the beginning, so you can create a new project or click the Projects Library tab to open an existing project. Here's a project we created in the previous lecture, so select that and click OK to open it. We haven't worked on it yet, so we have nothing on the workspace. The large window is called the workspace, and this is where your various routers, switches, and things like that are going to be connected to each other. So this is where you're going to create your topology. All right, so at the left left-hand side of the app, we have a toolbar called the Devices toolbar, aptly enough. Now, it shows you all of the nodes that are available. So if I click on this one, this shows me all of the router nodes that are available. If Installed and Available Appliances is the option selected in the combo box above, you'll see all the available options in the list. Here you see the installed nodes bolder, and the nodes not installed yet are grayed out. The second icon shows the switching nodes that are available. Again, the nodes ready to use are in bold, and there are switches embedded in the GNS3 app, and those are ready to use. Here's the Ethernet switch router that we created in the previous lecture. Now, the third one lists end devices, such as virtual PC nodes or a cloud node. If you select Installed Appliances from the combo box, you'll see the nodes that you can use at this very moment. If the node you want to use is not listed here, you've got to install it first. Now, perhaps you remember we installed a router, C3725, and it's available now. There are some nodes installed and available by default, such as this VPCS and Cloud. Now, the fourth menu option lists the security devices. No security device installed by default. The fifth menu item shows all the nodes together: routers, switches, end devices, etc. The last menu item adds nodes to each other. So pretty much anything that you can drag and drop into this working area right here is what the GNS3 considers to be a node, whether it be a router, a switch, a PC, or firewall. They all are considered as nodes from the GNS3 standpoint. And now is the moment you've all been waiting for. It's time to build our network in GNS3. So, I'm in my host machine, and you don't see the GNS3. It's closed at the moment, so I'll go to the Applications menu and click the GNS3 icon to run it. So let's create a new project, or you can use the project that we created before. Expand Routers from the Devices toolbar. As you see, Installed Items is selected from the combo box above. The only router available is C3725. That's what I imported a few lectures before. So I'll drag it and drop it into the workspace. From the Switches menu, drag an Ether switch router that we created before and drop it into the workspace. Now go to the end devices and drag and drop a VPCS here. VPCS are the end user computer simulations of GNS3. They're very lightweight and have a very restricted ability, but it'll be enough to test the network configurations. And now I'll just add a second VPCS. Okay. Now we have a router, an Ether switch, and two PCs in our network. They all have their default names on top, given by the GNS3 app. So now I want to design the network and label the devices accordingly. Click the Labels icon on the toolbar and put a label under the PC1. This PC will be in IP block of 192.168.10.0/24. Let's say it's the VLAN 10. Now, to create a new label, you can right-click on an existing one and select Duplicate. Right-click the label again and select Text Edit to edit the text. So let's put the second PC into VLAN 20, which is in the IP block of 192.168.20.0.024. Now click on the last icon on the Devices toolbar to connect the devices. Click the router, select the port you want to connect, and then select the switch and select the port of the switch again. I connect the Fast Ethernet 00 port of the router with the Fast Ethernet 11 of the switch. Good. So now connect the PC1 with the switch. Click Switch select Fast Ethernet 1, 2, and click PC1, and it already has a single network interface, Ethernet 0. Now do the same with a second PC, and use a port of the switch, for example, Fast Ethernet 1, 10. We connected all the nodes on the workspace, so now we can click the Connect icon to disable the Connect mode. Then in the toolbar, we have a button named Show Hide Interface Labels. If you click it when the labels are hidden, you'll see the labels of each interface connected. F stands for Fast Ethernet, and E stands for the Ethernet. And you can move the labels as you wish. Now let's start the nodes. We can start them one by right-clicking on them and selecting Start from the menu, or from the toolbar, click the green triangle to start all the nodes at once. Now all the nodes are running. So now's the time to create our network topology. I'll create 2 VLANs and add the PCs to their VLANs. First, we'll create the virtual LANs. Right-click on the switch and click Console. Good. Welcome to the command line interface of a Cisco Ether switch. Look familiar? So press Enter to get started. Type VLAN database and go there. You can use the Tab key to complete the keywords in this console. So instead, you can use the short form of the keywords directly, if the keyword is the only available option for that short form. So, for example, I wrote VLAN space DA and hit the Tab key. The keyword is completed, database. So that means that database is the only option here for DA. And as a result, if I type VLAN space DA and hit Enter here, I'd be in the VLAN database mode. Right, so here we are in VLAN database mode. To create VLAN 10, type VLAN ID number 10, name it. For example, IT, HR, whatever you want. I'll name it VLAN 10 and leave it at that. Hit Enter, and VLAN 10 is created. So similarly, let's create VLAN 20 with the ID number 20. Type Exit to exit the VLAN database mode. Now, as you exit, the changes are applied. So that's pretty cool. Okay, so let's go into the VLAN database mode again to check whether the VLANs were actually created. So type Show Current, and here are the VLANs we created a couple of seconds ago. VLAN 10 with the ID number of 10, and here's VLAN 20 with the ID number of 20. So type Exit again, and we're on the root of the switch console. So now's the time to configure interfaces and add the PCs to their VLANs. The first command we type is configure terminal. And as mentioned before, you can simply type CONF-T to enter configuration mode. Now we need to select the interface to configure. Type INT space F and hit Tab. F will be completed as Fast Ethernet. You see how that works? So now we can write the identifier of the switch port, 1/2. Alternatively, you can directly type F1/2 as seen in the GNS3 workspace. Now we are in the config mode of the interface F1/2, which just happens to be the port we connected to the PC1. Now to identify the mode of the port, type switch port mode access first. Then to assign the port to the VLAN 10, type switch port access VLAN 10, where 10 is the ID number of VLAN 10. No to shut down and exit. We exit from the ports config mode, but we are still in the terminal configuration mode. So while we're here, let's configure the other port, which is connected to PC2. Interface, fast Ethernet, 1/10. Switch port, mode access. Okay, well, right here, I want to show you a tip. You can use a question mark in any one of the commands. If you put a question mark after the mode, it says you can either use access or trunk here. An access port can only have one VLAN configured on the interface. It can carry traffic for only one VLAN, right? A trunk port can have two or more VLANs configured on the interface. That can carry traffic for several VLANs simultaneously. So, switch port access VLAN 20 goes right here. No shutdown and exit. Great, so we've configured the interfaces connected to the PC. So now let's configure the port connected to the router. INT for interface, F1/1 to enter the config mode of that interface. Switch port mode is trunk. Wait a second, and yes, the port has become a .1Q trunk. .1Q is the well-known name of the 802.1Q, which is the networking standard that supports virtual LANs, or VLANs, on an IEEE 802.3 Ethernet network. Now type switch port trunk encapsulation .1Q. No to shutdown and exit. Type exit again to exit the config mode completely, then type WR to make the configurations persistent. Excellent. Now, let's configure the router. Right-click on the router and select Console. The ports are being initialized now. Okay, entering into the config mode is the same. Type config terminal or simply conf T and hit enter. So the only interface of our router is fast Ethernet 00, so type interface F0/0, no IP address, no shutdown, and look at that, the port is up right now. So hit exit, and we'll exit from the interface for now. So now we're ready to configure the sub-interfaces, and the settings of the VLANs are decided here. To enter the sub-interface configuration, type interface fast Ethernet 0/0.1, where .1 identifies the sub-interface, right? Type encapsulation .1Q and a question mark to see the options. Look at that. Here, VLAN ID is one of the options, so type encapsulation .1Q10. Now type IP address 192.168.10.1, 255.255.255.0, and press enter. 192.168.10.1 is the IP address of the router for this VLAN, and 255.255.255.0 is the subnet mask of the network. So the IP block of the VLAN 10 will be 192.168.10.0/24. No to shutdown and exit. And here we are back in the configure terminal mode. So now we'll apply the same sub-config for VLAN 20. Type interface F0/0.2 this time. Encapsulation .1Q and the VLAN ID 20. So let's use the 192.168.20.0/24 IP block for this VLAN. So type IP address 192.168.20.1, 255.255.255.0, and no shutdown and exit. Now, exit again to exit the configure terminal mode as well, and type WR to make the configurations persistent. See what I mean? It's quite a process, but I'm glad you're hanging in there. because we haven't even got to the fun stuff yet. Now's the time to configure the network interfaces of the PCs. So right-click on the PC and select Console. If you place a question mark and press Enter, you'll see all the available commands in VPC Console. So as I mentioned before, this is an end-user computer simulation of GNS3, but not to worry, it's enough to test the configurations of the networks that we created earlier. And as you can see here, IP command is used to configure the IP settings of the VPC. And here you can show or use the shortcut SH, and that's going to print the information about the VPC. So type show IP to see the current IP settings. And as you can see here, VPC has no IP address at the moment. So type IP and a question mark. You'll see the options of the IP command. And as you can see here, you'll be able to assign an IP address using this command, and an example is given right there to help as well. So let's assign an IP address for the VPC. IP 192.168.10.2/24 to identify the subnet mask, and the gateway is 192.168.10.1. Perfect, it's our router. So when you press Enter, it checks to see if there's any duplication, and if everything's okay, it shows a summary, just like this one. Assigned IP address, subnet mask, and gateway. So now we can ping the router to check the configuration. Perfect. See, this is where we get all the answers. Now let's configure the other VPC, because that one is working perfectly, just the way we wanted it to. The steps are exactly the same. Right-click and open the console. Type IP 192.168.20.2/24, 192.168.20.1, and hit Enter. Ping the router to check the config, and here are the answers. All the answers you've ever been looking for, right? So, go to PC1 and ping PC2. You should be able to see the reply packets, just like these ones. And now, ping PC1 from PC2, and everything looks perfect on my side. What about you? Right as rain, right? Excellent. So let's move on. Okay, so now let's go one step further and add our colleague to the network. Are you ready for this? First of all, let me change the labels from the IP block to the IP address. And this one as well. And create the labels for VLANs. From the GNS3 main menu, select Preferences. In the tree at the left-hand side, you see that there is a VMware VMs. It's a menu item under the VMware menu. You got it? Okay, select it. Now, here I have a few VM templates that I've added before. You are supposed to have nothing here at the moment, unless you added something before as well. So in any event, click New, and a new VMware VM template window appears, and the VMware virtual machines are already listed in the combo box. So select Kali Linux 2018. Do not select Use as a linked base VM, because it's experimental at the moment and it could have some bugs that could just throw you off. So right here, let's just click Finish. All right, now we have a Kali template in GNS3. You can edit it here or delete it, just like the router that we added before. Okay, so its name is too long, so let's click Edit, change the name, and click OK, and OK again. Now we're ready to add it to our network. So from the Devices toolbar, if you expand the End Devices, that's where you see Kali. So drag and drop it into the workspace. And a label showing its IP address. I'll make it IP 10.3, and it'll be in VLAN 10. So click the last item in the device's toolbar to connect Kali to the switch. Click the switch, select the interface, and I'll select Fast Ethernet 1/3. And click Kali. Select the only option, Ethernet 0. Uh-oh, we got a problem. But no worries, we're troubleshooters here, right? It's not an unexpected situation. An error message appears at the top right corner. It says we have to stop the VM and allow GNS3 to change the attachment type. You can see the same message in the GNS3 console at the bottom. Go to Kali here and shut it down. And from the virtual machine menu item, select Shut Down. It's going to take about 2 minutes. But while Kali is shutting down, let's go to GNS3 and allow it to change the VM's attachment type. So from GNS3, the main menu, select Preferences, select VMware VMs at the left-hand side tree and click Kali and then click Edit. Now you can select the Network tab. And here there's a checkbox to allow GNS3 to override VMware adapter. So check it and click OK, and then OK again. And we're still waiting for Kali to be shut down. Okay, so let's try to connect Kali to the switch again. But we have another error message. It says, NAT is already configured on the network adapter. So let's allow Kali 1 to use any adapter. Okay, so I think I know the problem. Do? We'll find out. So we have to remove Kali from the workspace because this one has been added before we allow GNS3 to configure VMware's network interface. So now I'll add Kali again by drag and drop. Now connected to the switch. Okay, but before starting Kali, let me clear the GNS3 console. Now let's start Kali again. What? Another error message? Okay, no worries. I already knew all of these messages beforehand. I just want to show you what happens when the GNS3 needs to add Kali to it. So this message means that we need to have a custom network interface created in VMware and available to be used by GNS3. So now from VMware Fusion, I'll start Virtual Machine Library. From the main menu, select Preferences. If you're using VMware Workstation or Player, just go to the Preferences there. Now click Network. As you see, I have no custom interface at the moment. To be able to make changes, I'll click on the padlock icon, enter the password of my user, and now I can add a custom interface. So click the plus icon here, and VMnet3 is added. And leave everything with the default values because GNS3 will configure it for us. So click Apply, and now we can close these windows. So now let's go back to Kali and start from the GNS3 again. And sure enough, it starts. So log in as root user. And finally, we're on the Kali desktop. Now let's look at the network settings of Kali. This icon is a network interface. When you click it, you'll see the interface options. As you see, the current interface is Custom VMnet3. Alternatively, we can look at the network setting from the wrench icon, which brings us to a general settings panel, and then we can select network adapter from here. Great. So we attached Kali to our network physically. Now we have to make the configurations to make Kali a part of VLAN 10. So as you can see here, my Kali is not running at the moment. I'll go to Switches console to configure the connection. It'll be similar to configurations of the VPCs. Type conf t to enter the configure terminal mode. and then int F1/3 to configure the interface fast Ethernet 1/3, which is used for Kali. We have seen these before, so I'll just go through it quickly. Switch port mode access, switch port access VLAN 10, no shutdown, exit, exit again, go to the root, and WR to write the configuration to make it persistent. Okay. To check the current situation of the interfaces, we can now use show IP interface brief. Here's the interface of Kali, fast Ethernet 1/3. It's supposed to be up as shown here. However, if you've stopped the switch and started it again, your interface is probably down for now. As you can see here, my fast Ethernet 1/4 interface is up, which is supposed to be down, because nothing is connected to it. So I added another VM and removed it while I wasn't recording. That's why it looks like this. So let's restart the switch. What's expected at the end is your Kali port will be up and my F14 port will be down. So right-click on Switch, select Stop, and right-click again and select Start. Switch is up. Let's look at the interfaces again. Open console. The switch is initializing. Show IP interface brief. And as you see, fast Ethernet 1/3, the interface of my Kali is up as expected. F1/4 was up before the restart, and it's down now. And that's the expected result too. So I suppose your Kali port was down before the restart, and it's up now. If not, just go back and do the steps again. So now let's go to Kali and configure it. Since we don't have a DHCP in our network, we have to assign the IP addresses for the nodes of the network manually. So right-click on Kali and select Start. And Kali is started, and it's initializing. Log in with root user. My password is still TOOR. Okay, first, I want to check the network interface inside Kali. From the upper right corner, right-click to the network icon, and ETH0 is selected. That's exactly what I want. Now, to double-check, I'll go to the network interface from VMware menu, and yep, there it is, in custom mode, just as I wanted. Now, as I mentioned before, we have to assign the IP address, subnet mask, gateway, etc. manually. So open a terminal, and we'll use ifconfig to configure ETH0. All right, so ifconfig, the interface, ETH0, the IP address for Kali. I'll choose 192.168.10.3, subnet mask 255.255.255.0, and hit enter. Now to check the network, let's ping the router first. It was 192.168.10.1, and yep, there it is. We got the reply packets, and that's a good thing. Now you can use Control-C to quit the ping command. So let's ping another device in the same network, the VPC. Its IP was 10.2. Excellent. Right. So now just to triple check, let me go to the VPC and ping Kali from there. The IP of Kali is 10.3. Perfect. And we've got the reply packets to prove it. Let's go for a quadruple check. Okay, so I'll go to the routers console and ping Kali. The success rate is 100%. So as you see, the ping result is given in a different format in the router, and then the result is again just as we expected. So let's talk a little bit about the network and data link layer security. Why is it important, and how can we classify the network layer attacks, etc.? When the OSI model was introduced, there was no thinking of any type of security. Security just wasn't part of the design of either the OSI or TCP/IP models. Further, while there may be OSI layers, there are not necessarily protocols that correspond to them. You see, OSI was built to allow different layers to work without knowledge of each other. So any compromise in lower levels directly affects the higher levels. As a result, a system is as secure as its weakest link. In other words, security is as strong as the weakest link, right? So when it comes to networking, layer 2 is one of the weakest links. The protocols developed in the early years of the internet did not require a quality of service, QoS. For example, short delays in the protocols could be ignored. So the key principles of information security, CIA triad, confidentiality, integrity, and availability, were not integrated into the protocols, or they are really weak. So we can classify the network and data link layer attacks according to the effects of the attacks. Right? So these classes are denying the traffic between two hosts, sniffing or listening to the traffic, compromising the transferred data, and spoofing. TCP dump is a free open source, very common, and fast packet analyzer that runs under the command line. It prints out a description of the contents of packets on a network interface that match the Boolean expression given as a parameter. TCP dump has a lot of filtering options. We'll discuss some of them in the next slide. It can be preferred to the other packet analyzers, such as Wireshark, because it's so fast. It also supports some of the most common network traffic capturing format, PCAP. You can save the results as raw ASCII text in a document as well. So have a look at this. These are some of the parameters you can use with the TCP dump command. D, or list interfaces, prints the list of the network interfaces available on the system and on which TCP dump can capture packets. I, or interface, listens in on the interface. If unspecified, TCP dump searches the system interface list for the lowest numbered configured interface, excluding loopback, which may turn out to be, for example, ETH0. N means do not convert addresses, that is, host addresses, port numbers, etc., to names. V produces verbose output when parsing and printing. The more V, the more details. W writes the raw packets to specified file rather than parsing and printing them out. R reads packets from the file which was created with the W option or by other tools that write PCAP or PCAPing files. A prints each packet in ASCII, handy for capturing web pages. When parsing and printing, in addition to printing the headers of each packet, capital X prints the data of each packet in hex and ASCII. This is very handy for analyzing new protocols. So if you use the X option, the data of each packet is printed in hex. In addition to these options, you can filter the results in several ways. If you would like to monitor a specific protocol, such as TCP, you can use its name as the filter. You can capture packets to or from an endpoint residing in the network using net filter, or use host filter to see the packets of a host as a source, destination, or either one. Use the port to filter TCP or UDP packets sent to or from a specified port. Use port range to listen to ports in any given range. Now, if you use the SRC option, you can see only the packets where the target system is the source of the packets. Similarly, DST is used to specify the destination system. So, of course, you can use more than one filter in a command and set up the relation using and or as logical operators. For example, host is 1.1.1.1 and port is 80. Now, before running several TCP dump commands, let's examine the fields of a typical TCP dump output row. The row shown in the slide is a TCP packet. The first field is the time when the packet arrived, with a timestamp as hour, minute, second, and, well, the fractions of a second. So the second field is a protocol running atop the link layer, in this case, IPv4. Now for IP packets, the third field is the IP address or host name of the host sending the packet, along with, for TCP and UDP packets, the source port. The packet on the slide came from port 80 of the system 172.16.99.139. Now the fourth field is the IP address or host name of the host receiving the packet, along with, for TCP and UDP packets, the destination port. Flags is the TCP segment flag. The packet on the slide doesn't have any flags set other than ACK. ACK is the acknowledgement number in the packet. TCP dump shows sequence and acknowledgement numbers relative to the initial sequence number by default. Win is the source host's TCP window, and you see the options field. Length is the length of the data in the TCP segment. The length here is 0, so that means that no data is exchanged yet. So that's enough for now. Let's see TCP dump in action. Time for hands-on. So Wireshark is not a disaster movie set in the wide open sea. It is a free, open source, and the world's foremost network packet analyzer. And it is the de facto standard across system and network administrators. With a graphical user interface, Wireshark has the ability to listen and record traffic, as well as advanced filtering and reviewing options. So I'm going to visit a HTTP website first, then an HTTPS website. Let's go to Kali and run Wireshark. You can open a terminal screen and type Wireshark to start it. So these are the network interfaces that Wireshark is able to listen to. You can open another terminal screen and run the ifconfig command to see the network interfaces. So as you know, ifconfig stands for network interface configuration. So if we use the command without any parameter, it'll list all the interfaces available. We have eth0 as a network interface to listen to. So now I'll turn back to Wireshark and double-click eth0 to select it. Now Wireshark starts to listen to the Ethernet interface of Kali. And to create some traffic, I'll open a web browser and just visit an arbitrary website. And now we have enough packets to examine, so I'll click the Stop button at the upper left corner of Wireshark to stop listening to the traffic. So first, we have some DNS packets to find out the IP address of the visited site. We'll look at these kinds of packets soon, but right now let's just have a brief look. So a DNS query for the IP version 4, another DNS query for IP version 6. Don't worry about the versions right now. We'll cover them soon, I promise. These DNS queries are transferred as UDP packets in transport layer. The destination port is 53. This is the IP packet with the source and the destination IP addresses. So we'll go through the layers one by one, and we'll see all these packets, datagrams, and frames in detail. So we'll keep going. This is the structure of the Ethernet frame. First, there are two DNS queries for www.hackeracademy.uk. One for the IPv4 address, and the other one is for the IPv6 address. And because the website is redirected to hackeracademy.uk, there are two more DNS requests for this address. Next, DNS packets are the DNS query responses. This response is type A. That means it's an answer for the IPv4 request. And here's the answer, the IP address of the website. Now, DNS response packet uses UDP at the transport layer, IP at the network layer, etc. Here we have a TCP handshake between Kali and the web server. We'll also see this in detail later on. A SYN packet, a SYN ACK as a reply, and an ACK packet to complete the handshake. This is an HTTP GET request. We learned the IP address of the website, and now the system is ready to receive the web page. HTTP protocol and application layer. Now you can see the headers and the parameters of the request. TCP protocol and transport layer, source port, destination port, flags, etc. IP protocol in network layer. Here are the source and destination addresses. And Ethernet frame in layer 2. These are the TCP packets, which will build the HTTP response. So in this example, it's the web page. In other words, the response is transferred between the web server and our system as fragmented packets in transport layer. Here's the HTTP response, 200, okay. So the web page is received. And here's the data, which is our web page. These are the response details, response type, headers, etc. Here there's additional information produced by Wireshark, which says that the HTTP response is created by reassembling 5 TCP segments or packets. So now I'd like to show you the difference between that and HTTPS traffic. So I'll go to the browser and visit an HTTPS page now. But before visiting the page, let's start Wireshark. Here's the start button. Continue without saving. Okay, now we have a clean sheet. So I'll go to the browser and hit enter. Wow, lots of packets in milliseconds. So we've got plenty of packets to investigate. Just click the stop button once again. Okay, so the DNS request and the response packets first. Here is a response with an IPv4 address. Here there's a TCP three-way handshake between Kali and port 443 of Google's web server. And now a client hello TLS packet to start the TLS handshake, again between Kali and Google's server. Now to get rid of the other traffic records, I'd like to filter the results by the IP address of the Google server. Now, while the mouse pointer is on the server IP address, right-click and go to Apply as Filter and select the Selected option. So as you can see here in the filter bar, the IP address is assigned as the destination IP address. Now, we only have to see the traffic where the destination is the Google server. But we'd like to see both the incoming and the outgoing traffic. So I'll change the DST part of the filter to ADDR and click the blue arrow to activate the new filter. Now we can see the traffic in both directions. Okay, so here we are at the Hello TLS message. Here are the details of the message. TLS uses TCP protocol in transport layer. The Google server replies a server hello message as the second step of the TLS handshake. Then comes the certificate and server key exchange, and the server hello done message is sent by the server. Kali sends the client key exchange, Google server sends the new session ticket, and the encrypted communication starts. Here is some encrypted application data, which is meaningless for others who listen to the traffic. And as you can see here, the message is encrypted at the application layer, so you can still see the source and the destination addresses, the ports, etc. This is how an IPv4 packet is seen on Wireshark. So it's a DNS query response. The fields we mentioned are seen pretty clearly. Version is 4. Header length is 5 words, which means no options field. Total length is 96 bytes. MF and DF flags are not set. And you can see the source and the destination addresses and all the rest. So have a look at what you see here. There are a lot of packets that Wireshark captures in seconds. There are some requests and responses for them, broadcasts and their replies, and etc., etc. There is an easier way to follow a stream, although this is very entertaining. The stream is a collection of packets that form a network conversation from the beginning to the end, just like your favorite story. So I'm in Kali now, and I captured the traffic just for a little bit. And while I was capturing, I visited a website to create some HTTP traffic. And here are the results: DNS packets, TCP packets, HTTP packets, etc. So I'll select an HTTP packet, and it's the GET request. Right-click, go to Follow on the submenu, and here you see the TCP stream and the HTTP stream options are both enabled. So that means we can follow either the TCP stream or the HTTP stream. So let's click HTTP stream. Now the client packets are red and the server packets are blue. The GET request by Kali, 200 OK response by OWASP BWA. Now this is a return page in HTML format. So you can scroll down and we'll see some of the other requests and the responses in the same stream. And perhaps you're beginning to see that when you click on a link in a website or visit a website by typing its URL, there might be several consecutive requests and responses that you don't even realize. But in actuality, you don't need to know them as the end user, but we're not your typical end users now, are we? So let's keep going. From the combo box at the left-hand side of the bottom of the stream window, you can filter the conversation from one side to another or vice versa. So at the right-hand side, right, there is another combo box where you can select the output format. Now when you close the stream window and go back to the main window of Wireshark, you can see that the stream filter is applied right here. So I'll remove the filter by clicking this cross icon. Now I see the entire captured traffic again. That is why filters exist. So in typical traffic capturing on a network interface, there are a lot of packets received from and delivered to all over the network and, well, the internet as well. So let's see how we can take a picture of that network. Let's go to Kali and start Wireshark. You can start Wireshark from the Applications menu or open a terminal window and type Wireshark to start the app. Don't worry about the ampersand and the and of the command. Putting an ampersand at the end of a command causes the shell to run the process in the background. It's sort of multitasking. You can have many processes running, but only one in the foreground at any given point. The process in the foreground is the process that appears to have locked up the terminal. Whatever. The first message is because we are a super user on Kali. No worries. Okay, the welcome page of Wireshark asks which interface we would like to listen to first. So let's have a look at the interfaces of our system. To look at the interfaces and to remember the IP address of Kali, open a terminal and type ifconfig. There are two result sets of the ifconfig command, eth0 and lo. eth0 is the first Ethernet interface. Additional Ethernet interfaces would be named eth1, eth2, etc. Here we have only one. Now lo is the loopback interface. This is a special network interface that the system uses to communicate with itself. eth0 is the interface that we're interested in at the moment. Double-click to open the eth0 on the main page of Wireshark to start capturing the packets passing through our Ethernet interface. Now, to speed it up, let's create some network traffic. Open one of my virtual machines, OWASP BWA, and ping Kali. To stop ping command, press Ctrl-C, ifconfig, to learn the IP address of the machine. Now I go to another VM, Metasploit, and ping the last VM first. And then ping Kali. Here we have a lot of ICMP and ARP traffic at the moment. So let's generate some traffic. I open the browser in Kali and visit the website served by the OWASP BWA machine. And even more traffic. I visit nhs.uk, my favorite website. Okay, that's enough. Let's turn back to Wireshark. As you see, we have a lot of packets captured, and new packets arrive every second. ARP packets, TCP packets, TLS packets for HTTPS traffic, etc. Here we don't investigate the packets in detail. We want to learn about the systems which are interacting with us. So go to Statistics menu and select Conversations. There are 5 tabs in the Conversation window by default. And we're on the IPv4 tab at the moment. Here there are IP packets grouped by address A and address B. In each line, we see how many packets sent up to now, total size of the packets in bytes, number and size of the packets from A to B and from B to A, etc. There is traffic between 8.8.8.8 and my colleague. Now I know that 8.8.8.8 is the IP address of Google DNS, so I must have set the Google DNS as the DNS of my colleague. I'd like to look at the network config. And yes, my DNS address is 8.8.8.8. In the Ethernet tab, we can see the MAC addresses of the systems. The addresses full of Fs mean that the packet is broadcasted. ARP requests are the examples for these kind of packets. In the TCP tab, we can see TCP packets grouped by the addresses and this time by ports as well, because a system may have different interactions with any other system. For example, Kali may have HTTP traffic through port 80, and at the same time, it may have an SSH connection through 22 as well. Same as TCP. Packets are grouped by IPs and ports in the UDP tab. Here we have learned a lot of live systems, IP addresses, and MAC addresses just listening to the traffic go through our network interface. If you'd like to investigate the traffic between the two machines, select the line, right-click. If you choose Apply as Filter from the menu, only these kinds of packets will be seen in Wireshark. I'll choose Find at this time. As you see, Automatic Query String is prepared. I can navigate between the packets by clicking the Find button. Go back to the Conversation window. At the bottom right, there is a Conversation Types button. When you click on it, a lot of different protocols are listed. These selected 5 are the default selected protocols. You can add any protocol from the list. When you select one of them, a new tab is added to the Conversation window. Okay, so before we talk about how to expand the sniffing space, let me explain the active network devices and the routers, hubs, and switches. Hub is commonly used to connect segments of a LAN, which is a local area network, and a hub contains multiple ports. When a packet arrives at one port, it is copied to the other ports so that all the segments of the LAN can see all of the packets. Hub acts as a common connection point for devices in a network. Now, switch operates at the data link layer, layer 2, and sometimes the network layer, which is layer 3 of the OSI reference model, and therefore support any packet protocol. Now, LANs that use switches to join segments are called switch LANs, or in the case of Ethernet networks, switched Ethernet LANs. In basically all networks, switch is a device that filters and forwards packets between LAN segments. A router is connected to at least two networks, commonly two LANs or WANs, which are the wide area networks, or a LAN and its ISP, which is the Internet Service Provider's network. Router is generally located at gateways, the places where two or more networks connect. Using headers and forwarding tables, router determines the best path for forwarding the packets. And in addition, the router also uses protocols such as ICMP, Internet Control Message Protocol, to communicate with each other and configures the best route between any two hosts. So, in a word, router forwards data packets along networks. Now let's compare the hub and the switch, since both of these two devices have similar roles on the network. Each serves as a central connection for all of your network equipment and handles a data type known as frames. Frames carry your data. When a frame is received, it is amplified and then transmitted onto the port of the destination PC, which is typically a personal computer. The big difference between a hub and a switch is in the method in which frames are being delivered. You got that? In a hub, a frame is passed along or broadcast to every one of its ports. It doesn't matter that the frame is only destined for one port. The hub has no way of distinguishing which port a frame should be sent to, right? So passing it along to every port ensures that it will reach its intended destination. Now, this places a lot of traffic on the network and can lead to poor network response times. You can only imagine, right? Besides, the frame is received by the unintended nodes, which could be hackers. And in a cybersecurity point of view, what about the confidentiality? And additionally, on a 10100 megabit per system hub, it must share its bandwidth with each and every one of its ports. So when only one PC is broadcasting, it will have access to the maximum available bandwidth. However, if there are multiple PCs broadcasting, then that bandwidth will need to be divided among all of those systems, which will degrade performance for everybody. So in comparison, a switch keeps a record of the MAC, which is the media access control address of all the devices connected to it. With this information, a switch can identify which system is sitting on which port. So when a frame is received, it knows exactly which port to be sent to, without significantly increasing network response times. And in addition, unlike a hub, a 10100 megabit per second switch will allocate a full 10100 megabits per second to each of its ports. So regardless of the number of PCs transmitting, users will always have access to the maximum amount of bandwidth. That's important. So it's for these reasons that a switch is considered to be, well, let's say a much better choice than a hub, right? Good. So switches make it difficult to sniff the network traffic. In the past, the traffic was being sent to all ports with the hub technology. With switches, the traffic is directed only to the specified port. So a network device only receives its own packets, not the others. So we need to use some techniques to sniff the traffic of the other devices then, huh? These are some of the techniques to expand the sniffing space. You thought it couldn't be done. So we'll talk about SPAN, switched port analyzer, or port mirroring. So that's a method of monitoring network traffic. With port mirroring enabled, the switch sends a copy of all network packets seen on one port or an entire VLAN to another port where the packet can be analyzed. Port mirroring is supported by almost all enterprise-class switches I can think of. So, in other words, managed switches. It allows a particular computer to see the network traffic, which is normally hidden from it. You can monitor the entire traffic sent from the switch by copying its uplink port. Now, you have to have physical access and the admin privileges on that switch. So this method is often used to send the network traffic to the IDS, which is typically an intrusion detection system device. In a MAC address table overflow attack, also known as MAC flooding attack, within a very short time, the switch's MAC address table is full with fake MAC address and port mappings. Switch's MAC address table has only a limited amount of memory, and when that table is full, the switch cannot save any more MAC addresses in it. So once the switch's MAC address table is full and it can't save any more MAC addresses, it generally enters into a fail open mode, and it starts behaving like a network hub. Frames are flooded to all ports, similar to broadcast type of communication. So as an attacker in the network, you start to receive the frames of others. Address Resolution Protocol, ARP, or ARP, is a network layer protocol used for mapping a network address, such as an IPv4 address, to a physical address, such as a MAC address. A system asks for the owner of an IP address by sending an ARP request, and the owner of the IP address answers him with an ARP reply. What if the attacker replies first, before the owner of the IP? Once the attacker's MAC address is connected to an authentic IP address, the attacker will begin receiving any data that is intended for that IP address. This is the basic principle of ARP spoof attacks. ARP poisoning can be achieved because of the lack of authentication in the ARP protocol, so the attacker can send a spoofed ARP message onto the LAN. Would you like to make the attack much more powerful? I suspected as much. Then you've got to replace your MAC with the gateway. So every packet sent by the victim will be in your malicious hands. But we are ethical hackers, remember. Dynamic Host Configuration Protocol, DHCP, is a protocol used to provide automatic and central management for the distribution of IP addresses within a single network. It's also used to configure the proper subnet mask, default gateway, and DNS server information on the particular device. Now, similar to the other types of spoofing attacks, DHCP spoofing involves an attacker pretending to be someone else, in this case, acting as the legitimate DHCP server. Since DHCP is used to provide addressing and other information to clients, losing control of this part of the network can be very dangerous. In DHCP spoofing attacks, the attacker places a rogue DHCP server on the network, and as clients are turned on and request an address, the server with the fastest response is used. If the device receives a response from the rogue server first, the rogue server can assign any address as well as control which device it uses as a gateway. So a well-designed attack can collect traffic from local hosts to a rogue server that logs all traffic and then forwards out the traffic to the correct gateway or to the device. So this action would be almost transparent. Thus, the attacker can steal information almost invisibly. The foundation of a MAC flood is to make a switch behave like a hub. As I mentioned before, a hub sends the packet it receives to all of its ports. However, a switch sends the packet only to the target system. So if we can make the switch behave like a hub, then it would send the packet to all of its ports, and I could listen to the traffic even though I'm not the target. In a MAC flooding attack, within a very short time, the switch's MAC address table is full with fake MAC address and port mappings. Once the switch's MAC address table is full and it cannot save any more MAC addresses, it generally enters into a fail open mode and it starts behaving like a network hub. Ethernet switches uses MAC address tables to determine where to forward traffic on a LAN. So let's go step by step to understand how the MAC address table is built and used by an Ethernet switch to help traffic move along the path to its destination. Now suppose that all of the devices connected to the switch are powered on but have not sent any traffic yet. In this case, the MAC address table of the switch would be empty. Now suppose computer A wants to send traffic to the server. It prepares an Ethernet frame and it sends it off toward the switch. The first thing the switch would do when receiving the traffic is to create a new entry in its MAC address table for computer A's MAC address. Makes sense? The switch then performs a lookup on its MAC address table to determine whether it knows which port to send the traffic to. And since no matching entries exist in the switch's table, it floods the frame out all of its interfaces except the receiving port. Because the frame was sent out to all the switch's other ports, it is received by the target server as well. Then the server sends a new frame back toward the switch. The other systems which receive the frame do nothing. The switch receives the frame and creates a new entry in its MAC address table for the server's MAC address. It then performs a lookup of its MAC address table to determine whether it knows which port to send the server's traffic to, and in this case, it does. So it sends the return traffic out only on the port of computer A, without flooding. So this process repeats as devices continue to send traffic to each other. An important detail to remember is that the MAC address table timeout is typically short. So for example, default timeout duration of Cisco switches is 5 minutes. So an entry is left in the table itself only for that specified amount of time before the timeout expires and the entry is removed from the table. Let's look at the switching mechanism with a cybersecurity point of view. The mechanism has two weaknesses in it. First, when the target MAC address is not in the MAC address table, the frames are flooded out of all the ports, so unintended systems on the network are capable of sniffing these frames. The second weakness is that when the MAC address table is full, no new record is accepted. So what if I fill the table by announcing thousands of fake MAC addresses from a port of the switch? Most of the switches start to behave like a network hub in such a situation, which means they send each frame to all of the ports. So look at the page seen in the slide. This is the manual page of the macof command. Macof is a command line tool mainly used to flood the switch on a local network with random MAC addresses. So as I mentioned before, when the switch receives a frame, it creates a new entry in its MAC address table for these MAC addresses. Once the switch's MAC address table is full and it cannot save any more MAC addresses, it generally enters into a fail open mode and it starts behaving like a network hub. So let's see macof command in action. So here's a network that I created in GNS3. Well, the IP addresses are different from the one that I created in the previous lectures, but not to worry, it's completely identical with that network. So in addition, I've added some other VMware VMs, OWASP, Broken Web Applications, and Metasploitable in the same way with Kali. Now, just a little word of caution, while you're adding a VMware VM to a GNS3 network, do not forget to create a new custom network mode, such as VMnet2, because all VMs need a separate custom network mode. Remember that. Okay, so now I'll go to Kali. Since Kali is a part of the GNS3 network, its network settings is custom, so it's not in NAT mode right now. have a look at the IP address using ifconfig. Okay, so it's in 192.168.10.0.24 IP block. So now check the entire network. I go over to the other VMs and look at the interface configurations. These are the IP addresses of all the VMs. Now go to Kali and ping them. The results are pretty good. We got the reply packets for ping requests. So now I open another terminal screen and scan these two VMs and see the open ports and running services. So I'll simply use the nmap command with the IP address only. So it'll be a SYN scan, and the top 1,000 ports will be scanned. Here are the results. 10.11 has 9 open ports, and 10.12 has 23. And as you see here, telnet port of the 192.168.10.12 is open. So let's go to the VMs. 10.12 is Metasploitable, and 10.11 is OWASP BWA. Now, we know the telnet service is running on Metasploitable. So to create some traffic and let the switch fill the MAC address table, I'll start up a telnet connection from OWASP BWA to Metasploitable. Type telnet and the IP address of Metasploitable. Enter the username and password, which are already given as a welcome message here. And we got the session. Okay, so we can exit now. Now I'll go to the console of the switch and type show MAC address table dynamic to see the dynamic records of the MAC address table. Now here there are 6 port and MAC mappings for now. Run the command again, and now we have 2 rows. So it seems, by the look of this, that the MAC address table aging is 10 or 15 seconds. Okay, you ready for this? This is the time of MAC flooding. So now I'm in a terminal screen on Kali. Have a look at the manual of macof command first. So type man macof and hit enter. Macof is a tool that's used to flood the local network with random MAC addresses. And here are the options. I, to identify the network interface to attack. N, to specify the number of packets to send. D, to specify the destination system's IP address, etc. So let's create the command. Of course, the first command I'll send is macof. I, the interface that's used to attack, will type that in as eth0. D, the destination, the ether switch router. Now we're ready to run the command, so hit enter. And the MAC flood started, and macof sends tens of packets in seconds. Now let me go to the ether switch router console and look at the dynamic MAC address table again. You can call the last command by using the up arrow key. And as you see, there are a lot of rows for our fast Ethernet 1.0 port, which is used for Kali. So while macof is running, let's run Wireshark and try to listen in to the traffic on the telnet of Kali's own network interface. Now to see only the telnet traffic, type telnet in the filter box and click the blue button next to the box. Okay, no telnet traffic for now. Now I go back to the OWASP BWA VM and telnet to the Metasploit VM again. Telnet, the IP address of Metasploitable, username and password. Run a command. Okay. So back to Kali. You see the telnet traffic here. Kali is neither the source of the traffic nor the destination. It receives the telnet traffic. Now, this is a typical in hub behavior to send packets to each node, so we can say that our switch is behaving like a hub now, just like we predicted. So let's go ahead and stop Wireshark and the macgov command using Control-C keys. You can do that. These are the telnet packets. Since telnet is a clear text protocol by default, we can see the payload as well as the metadata. We can see every character in a different packet. So select one of them. Right-click, follow, and select TCP stream. So the red characters here are client packets. The blue characters are the server packets. Here's a credential, username, and password. An ARP spoof is performed replying to an ARP request before the real owner of the IP address. Because of the lack of authentication mechanisms in ARP protocol, you're able to set yourself as the owner of the IP in the source machine's ARP table. Okay, to understand the ARP spoof or ARP cache poisoning attack, let's remember the ARP protocol and its principles once again. Address Resolution Protocol, ARP, is a network layer protocol used for mapping a network address such as an IPv4 address to a physical address such as a MAC address. To simulate how the ARP mechanism works, we have a small network in the slide, a switch on top, and 3 computers connected to it. Computer A wants to talk to computer C. It puts an ARP request onto the wire, which happens to be broadcast. Essentially what it's saying is, who has computer C's MAC address? Of course, because it's a broadcast, every system on the network hears it. Does everybody respond? Well, what happens is that B hears that A is looking for the MAC address of computer C. B knows that it's not computer C and therefore does not respond to the broadcast. The broadcast, the ARP request, goes out to every system, but the only system that will reply is computer C with an ARP reply. In other words, computer A says, who has the MAC address of computer C? And although all the workstations hear the question, only C replies and says, I've got the MAC address of computer C, and this is what it is. So the ARP reply sends back the MAC address to computer A, and each of these machines start building an ARP table. These are how ARP requests and responses look in Wireshark. The first packet is an ARP request. As you see, it is broadcast. And the second packet is an ARP reply. The owner of the IP 207 answers with its MAC address. As you see, ARP request is broadcast throughout the network, and the first reply is trusted and accepted. Okay, so we have already seen the routine of the ARP protocol. Computer A sends an ARP request. The request is broadcast. The owner of the IP replies with an ARP reply, and both sides update their ARP tables. Now we have an attacker in the network. Okay, so this is how the ARP spoof attack works. Computer A wants to talk to computer C. If the MAC address table of computer C is not in the ARP table of computer A, it puts an ARP request into the wire, which happens to be broadcast. This is the point where all the computers on the network get the ARP request. So although it's not his IP address, the attacker replies the ARP request before the real owner. In this ARP reply, the attacker puts his own MAC address corresponding to the target IP address. Computer A receives the ARP reply and stores the address pair in its ARP table, and communication takes place. Oh yes, there's plenty more to do. There are several tools to perform an ARP spoof attack, such as ARP spoof, the command line tool which is embedded in Kali. But we're going to use EtterCap for the demonstration of the ARP spoof attack. EtterCap is a free and open source network security tool for man-in-the-middle attacks on LAN. It works by putting the network interface into promiscuous mode and by ARP poisoning the target machines. Thereby, it can act as a man in the middle and unleash various attacks on the victims. EtherCap has both a command line interface version and a graphical user interface version. Let's see them both in action. First, let me show you the command line version of EtherCap. So this is my network created in GNS3. I have a Kali, an OWASP BWA, and a Metasploitable VM in the network. So use ifconfig inside the VMs to check the IP addresses and the other interface configurations as well. So ping each other to be sure that they can communicate. Okay? Now I go to Kali, open a terminal screen, and do the same here. Check the interface configuration and ping other VMs. Yep, everything's okay. So let's look at the ARP table of Metasploitable. Type ARP-N and press Enter. So currently there are 2 records in the ARP table of Metasploitable, one for Kali and one for OWASP BWA. Now let me show you something. If you want to perform an ARP spoof attack, you should enable IP forwarding in your attacker system so that the packets will not end on your attacker system and be forwarded to the destination system. Otherwise, you'll block the traffic between the victim and the spoofed system. Check that out. So the IP address is managed by a variable IP forward, like in Kali. And to look at the file content, type cat/proc/sys/net/IPv4/IP forward and press Enter. Its value is 0. So to enable it, it has to be 1. So I'll change it. You can open the file with a text editor and change the value, but here I'll just simply use the echo command for this purpose. Echo 1 greater than sign the entire file name. So check the file again. And yes, its value is now 1. Now, please note that EtherCap enables IP forwarding automatically, even though you don't enable it manually. All right, I want you to know what's happening behind the scenes, so to speak. All right, so now's the time of the attack. Before creating the command, let's see the manual of EtherCap. So type man EtherCap and press Enter. So here's the short definition and the long description. Targets, options, M for man in the middle, MIT-M attack. So these are the MIT-M attack types. ARP is at the first line, and the others, ICMP, DHCP, etc. And here are the user interface options. T for the text-only interface. Anyway, let's just create the command. So first, the command itself, EtherCap. I, the interface, either 0. T for the text-only interface type. M to make it a MIT-M attack. And select the MIT-M attack type, ARP, column, remote. So the first IP specifies the IP address which will be spoofed. And the second IP address is the victim system. So that means there will be a row in the Metasploitable's ARP table with a Kali's MAC address and OWASP BWA's IP address. And that means when Metasploitable wants to send a packet to OWASP BWA, it will be sent to Kali instead, right? And with the help of IP forwarding, the packet will arrive at OWASP BWA finally. Now, please don't forget to use these slashes at the beginning and end of each IP address. The command is ready to run. So let's see what it does. Hit Enter. And here's a summary of the attack, the victims, interface type, etc. Now I'll go to Metasploitable, ARP-N, to see the ARP table again. And as you can see here, the first record is for Kali. So please look at the MAC address. And the second record is for OWASP BWA, but with the attacker's MAC address. Any packet sent from Metasploitable to OWASP BWA will visit Kali now. So let's create a telnet connection to port 80 of OWASP BWA. Type telnet OWASP BWA IP and the port 80. Now hit enter. Type get/http/1.0 and press enter twice. And here is the HTTP response, the main page of OWASP BWA. Now let's go back to Kali and see what happens. So these are all the TCP packets sent from Metasploitable to OWASP BWA. ACK packet, FIN packet, and scroll up a bit, and here's the telnet connection results. HTTP response. Keep going up. We can find some other critical data here too. And here's some credentials, for example. In the terminal screen where EtherCap is running, you can use Control-C to end the attack. So there it is, it stopped. Now go back to Metasploitable and look at the ARP table again. Now the IP address of OWASP BWA is matched with the correct MAC address. Now you might remember what I told you before that, well, I hope you remember everything that I told you before. But in particular, EtherCap has a graphical user interface as well. So let's have a look at EtherCap's GUI right now. Again, we're in Kali. Click Show Applications menu item and type EtherCap. And here you go, you'll find the EtherCap GUI app. So these are both EtherCap GUI apps. You can just simply click one of them. I want to show you, though, another way to start the app. From the upper left corner, Applications, go to Sniffing Spoofing Tools, and select EtherCap GUI. Okay, so here we are at the main panel of the EtherCap GUI. We'd better check the network, so I'll open up a terminal screen and ping the other VMs, Metasploitable and OWASP BWA. Yeah, everything looks okay. So go to the Sniff menu in EtherCap and select Unified Sniffing. Asking for input interface, ETH0 is good. Click OK. If you look at the EtherCap menu, it's totally different now. So go to Hosts and select Scan for Hosts. It's a kind of a ping scan to find out the devices of the network. It found 5 devices and added them to the hosts list. So go back to Hosts again, and now select Hosts Lists, and here's a list. Very nice. Works well. 192.168.10.11 is OWASP BWA. So this is the system that will spoof. So select it and click Add to Target 2. So 192.168.10.12 is Metasploitable. That's our victim. So we'll change its ARP table, select it, and click Add to Target 1. I think now we're ready to attack. What do you think? All right, so let's go to MIT-M and click ARP Poisoning. Okay, check the Sniff Remote Connections option and click OK. And the final step, go to Start and select Start Sniffing. So the attack has begun. Let's go to Metasploitable and see the attack result. To see the ARP table, type ARP-N and press Enter. The first row is for OWASP BWA, but the MAC address is Kali's MAC. To show it, now I'll ping Kali to create the ARP record. Run the ARP command again, and now I have another row for Kali. And both Kali and OWASP BWA have the same MAC address. Okay, you know the rest. The packets will be sent to Kali instead of OWASP BWA. So if you like, you can open Wireshark and collect the fruits of your labor. Enjoy it. Now, similar to the other types of spoofing attacks, Dynamic Host Configuration Protocol, DHCP, spoofing, involves an attacker pretending to be someone else, in this case, acting as a legitimate DHCP server. Since DHCP is used on most networks to provide addressing and other common information to clients, losing control of this part of the network can be dangerous. Dynamic Host Configuration Protocol, DHCP. Now, it's a protocol used to provide automatic and central management for the distribution of IP addresses within a network. It's also used to configure the proper subnet mask, default gateway, and DNS server information on the device. In most homes and small businesses, the router acts as a DHCP server. In large networks, a single computer might act as a DHCP server. In short, the process goes like this. The device, the client, requests an IP address from a router, the host, after which the host assigns an available IP address to allow the client to communicate on the network. So let's look at some of the advantages of using DHCP. A computer or any other device that connects to a network, local or internet, must be properly configured to communicate on that network. Makes sense? Since DHCP allows that configuration to happen automatically, it's used in almost every device that connects to a network, including computers, switches, smartphones, gaming consoles, you name it. Now, because of this dynamic IP address assignment, there's less of a chance that two devices will have the same IP address, which is very easy to run into when using manually assigned static IP addresses. Using DHCP also makes a network much easier to manage. From an administrative point of view, every device on the network can get an IP address with nothing more than their default network settings, which is set up to obtain an address automatically. So that's easy, gives them nothing to call the help desk about. The only other alternative is to manually assign addresses to each and every device on the network. You're not getting paid enough to do that. So because these devices can get an IP address automatically, they can move freely from one network to another, given that they're all set up with DHCP, and receive an IP address automatically, which is super helpful with mobile devices. Now, as a cybersecurity expert, you should know one more thing about the DHCP mechanism. The first device which replies to a DHCP discover request decides the configuration of the client. There is not any mechanism to authenticate the DHCP server. Similarly, a DHCP server tries to reply to all the DHCP requests, and again, there is no authentication mechanism for the clients who request an IP. You get it? I think you do. What if a hacker replies before the real DHCP? Or what if a client sends a lot of DHCP discovery requests by changing the MAC address each time? So let's have a look to see how a DHCP mechanism works in detail. Once a device is turned on and connected to a network that has a DHCP server, it will send a request to the server called a DHCP discover request. After the discover packet reaches the DHCP server, the server attempts to hold on to an IP address that the device can use and then offers the client the address with a DHCP offer packet. Once the offer has been made for the chosen IP address, the device responds to the DHCP server with a DHCP request packet to accept it. After which, the server sends an ACK packet that's used to confirm that the device has that specific IP address and to define the amount of time that the device can use the address before getting a new one. If the server decides that the device cannot have the IP address, it will send a NAC. Let's see the DHCP server mechanism in Wireshark. So Wireshark is already embedded into Kali and it's ready to use. In addition, I'd also like to show you how to download and install it in a Windows system. So right now I'm in a Windows 8 system. Open the internet browser and search for Wireshark for Windows, using those as the keywords. First link is the download page of wireshark.org. So let's click it. My Windows is 64-bit, so I'll download the 64-bit, which is the latest stable version. Click it and save the installer. Now, it takes less than a minute, unless your connection is a mess. You might want to look into that. Just kidding. Click to run it. The setup wizard opens. Okay, so simply it's a next, finish installation. No need to change anything. Wait until the installation finishes. Okay, so check this to run Wireshark now and click Finish. And welcome to the Wireshark and Windows interface. So now I will show you the DHCP mechanism in Wireshark. So let's run Wireshark, and you can see that it's listing the packets received by ETH0. So to demonstrate the DHCP mechanism, we need to ask for an IP address over at the DHCP server. From the bottom right corner, right-click to the network icon and select Open Network and Sharing Center. Click Ethernet 0 and then Properties. You'll have to scroll down a little bit and double-click IP version 4. And as you see here, the IP address is manually set for my Windows 8. So to start a DHCP request, I'll choose Obtain an IP address and DNS server address automatically. Those are my options. Now, before I click OK, I'll go to Wireshark and restart capturing by clicking the green button on the toolbar. So now Wireshark Windows will be cleaned. Continue without saving. So now go to the network status window and click OK. And we can close all the networking windows. So Wireshark captured the packets. Well, it's still capturing, but let's go to the top of the list to find the DHCP packets. So here the DHCP Discover packet is right here at the top of the list. When we look at the ports in the UDP header, we see that the port 68 is used to send DHCP Discover packets. So let's go back to the filter box and type UDP port equals 68. And now we have the DHCP packets only. So the first packet is DHCP Discover. And as I mentioned before, it's broadcast. Source IP is all zeros because we don't have an IP address at the moment. Destination IP is all ones, 255.255.255.255 because it's a broadcast packet. And right here is Bootstrap Protocol, which is an application layer protocol used by DHCP mechanisms. The second packet is a DHCP offer packet sent by the DHCP server, 172.16.99.254 to the Windows system. Destination IP is 172.16.99.233, which is offered to the DHCP server. So in here, the destination MAC address is important. That's what's going to be targeted according to the MAC address. So as you see, the destination MAC address of the DHCP offer packet is the same as the source MAC address of the DHCP Discover packet. Now the third packet is the DHCP request sent by the Windows system. It's still a broadcast packet and the source IP is still all zeros. The message is request and the requested IP address is an option 50. So if you expand it, you see the requested IP address. And it's the same as the offered IP address, 172.16.99.223. The last packet is DHCP-ACK, sent by the DHCP server to the Windows system. This packet completes the DHCP mechanism successfully. So from now on, the IP address of our Windows system is 172.16.99.223. In DHCP spoofing attacks, the attacker places a rogue DHCP server on the network. There are two main features of the DHCP mechanism that emerges the DHCP spoofing attack. First, there's no authentication process and priority in the DHCP mechanism. Second, as clients are turned on and request an address, the server with the fastest response is used. So if the device receives a response from the rogue server first, the rogue server can assign any address as well as control which device it uses as a gateway. So a well-designed attack can funnel traffic from local hosts to a rogue server that logs all the traffic and then forwards that traffic out to the correct gateway to the device. And this action would be almost transparent, right? Thus, the attacker can steal information pretty much invisibly. How are you going to find that? That's why you're here. Let me clue you in on another important point. While setting up a rogue DHCP server, we cannot be so sure whether the client received the settings of the rogue server or the legitimate server. That's why it's way better to use the DHCP spoofing attack with the DHCP starvation attack. All right? In a DHCP starvation attack, an attacker broadcasts a large number of DHCP request messages with spoofed source MAC addresses. If the legitimate DHCP server in the network starts responding to all these bogus DHCP request messages, available IP addresses in the DHCP server scope will be depleted within a very short span of time. Now, once the available number of IP addresses in the DHCP server is depleted, network attackers can then set up a rogue DHCP server and respond to new DHCP requests from the network DHCP clients. By setting up a rogue DHCP server, the attacker can now launch a whole DHCP spoofing attack. So here is how we can perform a DHCP spoof attack together with DHCP starvation attack. So we'll create a lot of DHCP discovery packets to request new IP addresses from the DHCP server. DHCP server replies to these requests. IP address space is limited. For example, a Class C subnet has about 250 IP addresses available. So since the IP addresses are used for fake MAC addresses, there aren't any more IP addresses for legitimate clients. DHCP cannot respond to the new requests, and the clients which cannot have IP addresses become out of service. So now we'll set up a rogue DHCP server, which is the only server to respond to the client's IP address requests right now. The rogue DHCP server starts distributing IP addresses and other TCP IP configuration settings to the network DHCP clients. TCP IP configuration settings include default gateway and DNS server IP addresses. So now we can replace the original legitimate default gateway IP address and DNS server IP address with our own IP address. Once the default gateway IP address of the network devices are changed, the network clients start sending the traffic destined to outside networks to the attacker's computer. The attacker can now capture sensitive user data and launch a man-in-the-middle attack. So let's see how we can perform a DHCP starvation attack and consume the DHCP pool using Yersinia. Yersinia is a network tool designed to take advantage of some weaknesses in different network protocols. The protocols currently implemented in Yersinia are shown in the slide. Now we're going to use our VMs in NAT mode during this demo. So I'm on my host machine and open the virtual machine library. This is the Kali that I'll use. So click this icon to see the VM settings. Click the network adapter icon. It says Internet is shared with my Mac, so if you look at the explanation in the right-hand side of the frame, it means the VM is in NAT mode. So this is what we want, so just leave it as it is. The Connect network adapter is selected, so Kali is ready to use with the NAT network connection. So Windows 8 is the other VM that I'll use to demonstrate DHCP starvation attack. Let's have a look at the network settings of Windows as well. Yeah, it's in NAT mode, and the network adapter is connected. So I'll disconnect the network adapter by clicking here, because I just want to show you that the DHCP of VMware is working properly. So I want to add a second network interface for my Windows system. Click Show All and go to the Settings menu and click on Add Device at the upper left-hand corner. Select Network Adapter and click Add. The details of the new adapter are listed here. The NAT mode is selected by default already. So uncheck the Connect Network Adapter box for now. Okay, so as you see, we have two network adapters for the Windows system. Both of them are in NAT mode and are disconnected. So now I'll start the Windows 8 system. Log in, and sure enough, it's ready. Right-click on the network icon at the lower right corner and select Open Network and Sharing Center. And right there, we don't have an active network at the moment. That's to be expected. So now I connect the first adapter and activate the network. In VMware Fusion, you can see and change the setting in several ways. If you use the VM in full screen mode like I do, just go to the upper side for VMware Fusion menu. There it is. And if the menu does not appear, just press Command-Control buttons together. Right, so this is the default setting of VMware Fusion to turn back to the host system when you're inside a VM. And these are the network adapters. When you click on them, you'll see the short menu for network adapter. And here you can connect or disconnect the network adapter, change the network mode, NAT bridge, or host only, and you can use this pop-up for the network adapter settings. Now, the second way to see and change the network settings is to click the settings icon. Then select the adapter to see the settings. So the third way is to go to the virtual machine menu. Go to the network adapter, and you'll see the short menu of the adapter. Now go to the first network adapter icon and click on the Connect Network Adapter menu item. And now you see in the Network and Sharing Center window, we now have an active network connection. So click the network name and the Details button. Here are the connection details, and right there it is. DHCP is 172.16.99.254, and it assigned an IP address for the VM 172.16.99.221, as well as the gateway and the DNS address. Now I'll go back to Kali and open a terminal screen. Using the ifconfig command to see the network interface configuration, and sure enough, it has the IP address. So ping the Windows 8 system to validate the network, 221. Okay, we receive the ICMP reply, so everything looks okay. Now is the time for Yersinia. So type man Yersinia and hit enter to see the manual. And right here in the manual, Yersinia is a framework for performing Layer 2 attacks. And here's a list of protocols implemented in Yersinia. Scroll down, you'll see the options. We can use uppercase G to start a graphical interface. So let's go ahead and use it in graphical mode. You can press Q to quit from the manual and turn back to the terminal. Now type Yersinia uppercase G, and press Enter. So this is the graphical user interface of Yersinia. Before running the attack, let's open Wireshark and monitor the network packets to see what happens when we start the attack. You can type Wireshark in terminal to start it, or just click the Wireshark icon. To select the interface to listen, double-click ETH0. And to discard the different packets and focus only on the DHCP packets, we can filter the packets. In the filter box, type bootp and hit enter. So bootp is the short form of Bootstrap protocol, which I mentioned earlier. It's basically a computer networking protocol to automatically assign an IP address to network devices from a configuration server. And obviously, it's used by the DHCP server. Now we can turn back to Yersinia and prepare and run the attack. So click Launch Attack. That's the link at the upper left-hand corner. The tabs in the window are the implemented protocols. Choose DHCP and select Sending Discover Packet. Now click OK. As soon as we click the button, Yersinia starts sending dozens of DHCP requests in a second. It'll keep sending the packets till we stop the attack. Now look at the Wireshark window. These are the DHCP Discover packets sent by Yersinia. So now, while Yersinia is sending the DHCP Discover packets, let's activate the second interface of the Windows VM. And let's see if the DHCP server assigns an IP address for the second interface. All right, so we're in the Windows VM now. Go to the second network adapter, click Connect Network Adapter 2 to activate the second interface. Now, do you remember what happened when we activated the first interface? We saw the new network activated, but now there is still no network because the DHCP server is busy replying to the request created by Yersinia. It's not going to answer the Windows 8 second interface. So let's turn back to Kali and stop the attack. In Yersinia's interface, just click List Attacks and then click Stop or Stop All. In the Wireshark window, look at the bottom of the packets list. We now have a complete DHCP sequence. Discover, Offer, Request, and ACK packets. In the Windows 8 VM, we now have the second network. The first one was Ethernet 02. This one is Ethernet 0. Click on it. In the status window, click on Details. The second interface has an IP address now, assigned by the DHCP server. Now, to be honest, there are a number of different types of VLAN attacks in modern switch networks. The VLAN architecture simplifies network maintenance and improves performance, but it also opens the door to abuse. So it's important to understand the general methodology behind these attacks and the primary approaches to mitigate them. VLAN hopping enables traffic from one VLAN to be seen by another VLAN. Sounds kind of fun, huh? So as we've already seen before, a virtual local area network, virtual LAN or VLAN, is a group of hosts with a common set of requirements, which communicate as if they were attached to the same broadcast domain, regardless of their physical location. VLANs work by applying tags to network packets and handling these tags in networking systems, creating the appearance and functionality of network traffic that is physically on a single network, but acts as if it is split between separate networks. Capiche? So let's take a moment and remember the reasons of why we're using VLANs. Security. Groups that have sensitive data are separated from the rest of the network. Cost reduction. Cost savings result from less of a need for expensive network upgrades. Higher performance. The number of router hops reduces and the apparent bandwidth for network users increases. Broadcast storm mitigation. Every VLAN only receives its own broadcast packets. Improved IT staff efficiency. As we were talking about before, VLANs make it easier to manage the network. It also simplifies the company's management. Another type of VLAN hopping attack is known as double tagging attack. This type of attack takes advantage of the way that hardware on most switches operates. Most switches perform only one level of 802.1q de-encapsulation, which allows an attacker to embed a hidden 802.1q tag inside the frame. This tag allows the frame to be forwarded to a VLAN that the original 8021Q tag did not specify. An important characteristic of the double tagging VLAN hopping attack is that it works even if trunk ports are disabled, because a host typically sends a frame on a segment that is not a trunk link. So let's see how the double tagging VLAN hopping attack is performed step by step. The attacker sends a double tagged 802.1Q frame to the switch. The outer header has the VLAN tag of the attacker, which is the same as a native VLAN of the trunk port. Normally, a switch port configured as a trunk port sends and receives VLAN-tagged Ethernet frames. Native VLAN is the only VLAN which is not tagged in a trunk. In other words, native VLAN frames are transmitted untagged. The assumption here is that the switch processes the frame received from the attacker as if it were on a trunk port. In this example, the native VLAN is VLAN 1. The inner tag is the victim VLAN. In this case, it's VLAN 20. The frame arrives on the switch, which looks at the first 4-byte 802.1Q tag. The switch sees that the frame is destined for VLAN 1, which is a native VLAN. The switch forwards the packet out on all VLAN 1 ports after stripping the VLAN 1 tag. On the trunk port, the VLAN 1 tag is stripped, and the packet is not retagged because it's part of the native VLAN. At this point, the VLAN 20 tag is still intact, and it has not been inspected by the first switch. The second switch looks only at the inner 802.1Q tag that the attacker sent and sees that the frame is destined for VLAN 20, the target VLAN. The second switch sends the frame onto the victim port or floods it, depending on whether there is an existing MAC address table entry for the victim's host. So the best approach to mitigating double tagging attacks is to ensure that the native VLAN of the trunk ports is different from the VLAN of any user ports, right? In other words, do not let the users use the native VLAN. In fact, it's considered a security best practice to use a fixed VLAN that is distinct from all user VLANs in the switch network as the native VLAN for all 802.1Q trunks. So remember that while performing a penetration test, we should always test the network devices, whether they're vulnerable to attacks, all the ones we've mentioned up till now. Of course, we have to discover the network devices and the services running on them first. So let's see how we discover network devices and their services, and what else we can do to attack these services. Come on, it'll be fun. So, as you already know, the first step of a penetration test is always reconnaissance. In other words, gathering the information. So how can we collect information about the network devices? The answer is the same with a reconnaissance of all the other parts of the penetration tests. We can scan the network and find the network devices according to the fingerprints or operating systems of the devices found. For example, if the operating system of a device is Cisco iOS, it's most probably a network device, such as a switch or a router. Sniffing is another way to collect data about the network devices. You should always especially focus on the clear text services, such as Telnet. Now, one of the brilliant ways of reconnaissance is analyzing the documents collected throughout the penetration test. In a typical penetration test, you probably find a lot of sensitive information by just looking at the file servers, shared files, and email backups or unprotected ASCII files of compromised admin personal computers. So as we were saying before, the most common services open in the network devices are SSH, Telnet, HTTP, HTTPS, and SNMP. And the default ports of these services are listed in the slide. I want to call your attention to these are the default ports, right? So they don't have to run on the specified port. You can run an SSH service on port 443 or an HTTPS service on the port, 4321, etc. You can discover more details about the network devices by analyzing these services deeply. Right, so now, to have the correct results and discover even more, you should always scan network with OS discovery and version detection options. So if you look at the example in the slide again, you see an nmap command. Nmap is a security scanner, which is used to discover hosts and services on a computer network. In the same sample command shown, the O parameter is used for OS detection, while S_V is used for version detection. Great. So just listen to the traffic. We can gather some information about the network devices here. The protocols which use clear text communication are especially important because you can see the payload data transferred between the endpoints. The most important clear text protocols are Telnet, Cisco Discovery Protocol, Spanning Tree Protocol, Routing Protocols, VLAN Trunking Protocol, and Simple Network Management Protocol. So let's scan the router according to the criteria that we talked about up till now. In Kali, I opened a terminal screen, so I'll use the nmap to scan the router, but first, let's go ahead and ping the router to check the network. And it's okay. So nmap is the command itself, S_S to make it a SYN scan. A SYN scan is a kind of TCP scan where three-way handshake is not completed. But please refer to my Network and Vulnerability Scan for Hacking by Nmap and Nessus course for more details about the nmap and those scan types. Target IP is our router. S_V is for the version detection of the open ports. O for the operating system detection. Reason is to force nmap to tell the reason of its decisions. And P is for the ports. So let's scan SSH, Telnet, HTTPS, HTTP, and SNMP ports. Now hit enter. So that took 15 seconds. Seems the only port open is the Telnet. Here's the OS details. It is a Cisco device and one of these series. A password cracking attack is either online or offline. So let's talk about this classification for a little bit. So there are a lot of password cracking tools out there, and I'll list some of them here. Hydra is a command line online cracking tool. We'll put our hands on it in a few minutes. Cain Enable is a password recovery tool for Microsoft operating systems. It allows easy recovery of various kinds of passwords by sniffing the network, cracking encrypted passwords using dictionary, brute force, and cryptanalysis attacks, recording VoIP conversations, decoding scrambled passwords, recovering wireless network keys, revealing password boxes, uncovering cached passwords, and analyzing routing protocols. Does a lot, huh? John the Ripper is a fast password cracker, currently available for many flavors of Unix, Windows, DOS, and OpenVMS. It's one of the most popular password testing and breaking programs, as it combines a number of password crackers into one package, auto-detects password hash types, and includes a customizable cracker. Hashcat is another password recovery tool. The developers of the tools claim that it's the fastest password cracker in the whole world. It can basically use GPU as well as CPU, where the GPU is, well, let's face it, far more powerful in processing. So the OPH crack is a free Windows password cracker based on rainbow tables. It's a very efficient implementation of rainbow tables done by the inventors of that method. It comes with a graphical user interface and runs on multiple platforms. Simple Network Management Protocol, SNMP. It's an Internet standard protocol for collecting and organizing information about managed devices on IP networks, and for modifying that information to change device behavior. Devices that typically support SNMP include cable modems, routers, switches, servers, printers, and a lot of other devices. It uses the port 161 by default. It's an application layer protocol and uses both TCP or UDP protocols in transport layer. SNMP v1 is the original version of the protocol. More recent versions, SNMP v2c and SNMP v3, feature improvements in performance and flexibility and, of course, security. If SNMP service is enabled in a network device, and if it's not configured in a secure manner, we're able to gather a lot of information using the service. So let's look at our router and see if the SNMP service is enabled. If not, we'll enable it, and then, well, we're going to have some fun. Okay, so now we are back in GNS3, and all the devices are up and running. So go to the router console. Just right-click on it and select Console. The console is already open here. Now to test the SNMP service, type Show SNMP and hit Enter. SNMP agent is not enabled at the moment, so let's enable it. Configure terminal. You can complete the command by pressing Tab after a few initial letters, or if there's only one option with those letters, then you can use it as it is. So in here, you can use Configure Terminal command, just like conf t. SNMP server enable traps to enable SNMP trap. Let me just tell you that SNMP traps are alert messages sent from a remote SNMP-enabled device to a central collector, or the SNMP manager, right? A trap might tell you that a device is overheating, for example. This will be enough to enable SNMP service. So type End to exit from the configuration mode. And again, type Show SNMP and hit Enter, and look at that, the SNMP service is enabled now. So you'll see a brief summary of the service. Now we should be able to identify SNMP community strings. The SNMP community string is like a user ID or password that allows access to a router's or some other device's statistics. SNMP community strings are used only by devices which support SNMP version 1 and SNMP version 2c protocol. SNMP v3 uses username password authentication along with an encryption key. So once again, enter the configure terminal mode. Type in SNMP server community in anywhere the command. You can just put a question mark to get help about what's expected. So here it waits for the community name. So let's just use public, which is a commonly used name for read-only communities. And last, the community type, RO for read-only. So now that we're on a roll, let's create another community with a write privilege this time. Let the name be private, and I'll put a question mark here to see the options. So we chose RO for the previous community. Now let's use RW to give community the right access. End to exit the configuration mode, and WR to save that configuration. Now let's go back to Kali to test the SNMP service. So there's already a terminal screen inside my Kali, and here there's an Nmap query to query the most used ports, including the SNMP default port 161. The query was run before we enabled the SNMP service, but as you see, The SNMP port was closed then. So let's run the query again. Call the same query by clicking the up arrow. Here it is, the target IP, and the ports to scan. So in this query, S identifies the scan type as a SYN scan. It's a scan type to scan TCP ports. O is for OS detection. V is for version detection. Reason is to see the reason why the port is signed as open or closed. Now press Enter to run the query. Wow, look at that. The port 161 is supposed to be open, but it's not. Oh, okay, I know the reason. We scanned the TCP ports, but SNMP uses the UDP ports in general. So if we scan the UDP port 161, we'll see that it's open. Okay, we'll scan the port UDP 161 in the next lecture. As I mentioned before, Nmap, Network Mapper, is a free and open source utility for network discovery and security auditing. Many systems and network administrators also find it useful for tasks such as network inventory, managing service upgrade schedules, and monitoring host or service uptime. So let's analyze the SNMP service of our router using Nmap. So remember, in the previous lecture, we scanned the TCP ports, and we saw that the port TCP 161 was closed. But we enabled the SNMP service in the router with the default values, so it's supposed to be open. SNMP uses the UDP protocol in general, so we should check the port UDP 161 as well. So let's create another Nmap query. This time around, we'll use SU to run a UDP scan. Identify the ports scanned by P as a parameter, 161 and 162, V for version detection, and finally, the IP address of our router. Great. UDP scans take a little longer than TCP scans in general. So it took about 2 minutes, and here are the results. Both UDP port 161 and 162 are open as expected. Now, Nmap has a scripting engine and has a lot of useful scripts that come with the Nmap tool by default. The extension of Nmap scripts is .nse, so let's find a few using the locate Linux command, locate *.nse. Here are the Nmap scripts. Now I want to filter the scripts written for just the SNMP service. Recall the command, put a pipe, type grep SNMP, and hit Enter. It'll show only the lines which contain SNMP as the keyword. The SNMP brute script is to find the community names of the service using the brute force attack. So let's create a new Nmap query to run this script. Nmap U to scan UDP ports, P161 to scan the port 161, IP address of the router, script to run the script, and finally, the name of the script, SNMP brute. And here's the result. Nmap found 2 community names, public and private. That's just perfect. Now, I just wouldn't be me if I didn't show you another way to collect information from the SNMP service. So let's have a look at the SNMP check command line tool. SNMP check allows you to enumerate the SNMP devices and places the output in a very human-readable friendly format. It could be useful for penetration testing or systems monitoring. So here we are in Kali again with a terminal screen. If you write SNMP and hit Tab twice, you see the Kali commands, which start with SNMP. So this is our command, SNMP check. Let's look at the manual of the command first. So type man SNMP check, and hit Enter to access the manual page. Name of the command, and options, P to identify port, C to identify community, W to detect write access, all that. And of course, you can exit the manual by pressing Q. Okay, so let's build a command. SNMP check. We don't need to identify the port because it's already 161 by default. C to identify community. Now we know that our router has two communities, public and private. Let's look at the write privilege of the private community. And finally, the IP address of our router. The result output is very long. It's the configuration of the router. So let's scroll up to see the first lines of the result set. Okay, so here is the write access check result. And as you can see here, the private community is write access permitted. What else do we have in the output? System information, network information, the status of the switch ports of the router, network IPs, routing table, and the list of open UDP ports. So I'll introduce you to the last example of compromising SNMP. Let's try to grab the SNMP configuration of the Cisco router using Metasploit framework. Metasploit project is the most used penetration testing framework of, well, the whole world. It can be used to test the vulnerability of computer systems or break into remote systems. Its best-known sub-project is the open-source Metasploit framework. That's a tool for developing and executing exploit code against a remote target machine. So here we have our network prepared by GNS3 again. We'll perform this demo on this network, because look at that, it's right here. So go to Kali and open a terminal screen. Type MSF console and press Enter to start Metasploit Framework's console application. So now we have a shell-like MSF environment. We can run the MSF console commands in this environment. Now, because it's the subject of exploitation and post-exploitation course that I did, I won't go into deep detail about Metasploit right now, but I will talk about some certain applicable points. We'll use a module to collect the configuration of the router. I don't remember the exact name of it, so why don't we search for Cisco and config keywords. We find an auxiliary module. Auxiliary modules are not to exploit a vulnerability, but to gather some information and to help the pen tester figure out the systems and the vulnerabilities. So use the use keyword with the entire module name. Command prompt is changed as the module name now. Type show options to see the options we should set before running the module. The community option is required and is public by default, but let's set it as private. Set output directory option to save the results in a file. So I'll choose the desktop as the output directory. Now set the remote host, the IP address of the target router. Our port is 161 by default, which is definitely okay with us, and leave the other options with the default values. Now we're ready. Type run to run the module. Auxiliary module execution completed, and the configuration file is saved to the output directory, in this example, of course, to the desktop. So here's the file. Double-click it to open it. Welcome to the configuration of the router. We don't have any credential on our router yet, so let's close the file now. Go to the router console and create a user. Then collect the config file again and just see how a user is saved in the config file. So I'm in the GNS3 emulator in my host system, which is a Mac, and I'll go to the console of the router and just create a user. Of course, we need to enter the configure terminal mode first. So type username. Well, to understand the command, I'll put a question mark at the end of each word. The username is expected. Let's give it an exceptional username. How about Cisco? Question mark once again. These are the next options. Okay, we want to specify a password for the user. So we can use either password or secret as the keywords to set a password. I'll tell you their differences soon, but let's just use password as a keyword for now. Yeah, let's just keep the password simple for now, 12345. Or wait, maybe that's just too popular. In any event, just press enter. Now, to identify the privileges of the user, type username Cisco privilege 15, where 15 stands for the complete control over the router. Okay, now let's go to Kali and run the auxiliary module again. So it's all finished, and the output file is created. If there's a file with the same name, it's overwritten, so just be aware of that. Double-click on the file, and look at the configuration of the router again. And look at that, the entire configuration of the router. And look at the rows more carefully. Yep, there it is, the credential we created just a couple of minutes ago. So as you see, the password is saved as clear text, and as hackers, we learned the username and password remotely. Now, does it have to be like this? I mean, are the credentials of the users always stored as clear text in the Cisco config? The answer is, of course not. So I'm going to show you the ways to keep the password data secure. Better pay attention. The vulnerabilities we may come across during the penetration tests are as follows. Lack of access control lists. Network devices provide basic traffic filtering capabilities with access control lists. Access control lists can be configured for all routed network protocols to filter the packets of those protocols as the packets pass through a router. You can configure access control lists at your router to control access to a network. Access lists can prevent certain traffic from entering or exiting a network. Insecure password methods. While creating a credential for a network device, there might be more than one method to create the password for the account, and some of these methods are not secure. Either the passwords are stored and transferred as clear text, or they are encoded or encrypted by an easy-to-crack cipher. Web interfaces to manage the network device. Using web services and interfaces to manage network devices brings new responsibilities. First of all, you should use HTTPS instead of HTTP to avoid clear text traffic. Hardening the web application against the vulnerabilities, such as SQL injection and XSS. Implementing an appropriate authentication mechanism and access control are some other concerns of securing a web application. Insecure SNMP versions. SNMP depends on secure strings or community strings that grant access to portions of devices' management planes. Abuse of SNMP could allow an unauthorized third party to gain access to a network device. SNMP v3 should be the only version of SNMP employed because SNMP v3 has the ability to authenticate and encrypt payloads. When either SNMP v1 or SNMP v2 are employed, like I was saying earlier, an adversary could sniff network traffic to determine the community string. You saw that happen. You did it yourself. This compromise could enable a man-in-the-middle or replay attack. Telnet. Telnet data is sent in clear text. So as you know, a man-in-the-middle is able to read the traffic. It's certainly a good idea to use, for example, SSH to access network devices, especially when going through a public network like Internet. And as you're probably aware, SSH would encrypt all the data sent between the client and server, and even if someone gets a hand on the data, it's of absolutely no use. Non-complex passwords. Even if you use the right password methods, you should always use complex passwords because you are always under the risk of password cracking attacks such as brute force and dictionary attacks. So beyond the penetration test, we should perform security audits on the network devices to be sure whether they are configured according to security criteria. Typically, these audits will include password creation methods, identity management mechanism, access control lists, SNMP security, and switch port security. In Cisco routers, there are two main methods to create passwords for users and services: the password and the secret methods. So let's see these methods and each of their features on the router. So here we are in GNS3, and we're back on our network. Right-click the router and select Console to reach the router, unless it's already open. If you have a console and you select the console option from the right-click menu, it opens another console. Configure T to enter terminal configuration mode. Let's create a new user. Username. I'll name it as Cisco1. And I'll put a question mark to see the options. To create a private authentication keyword, we have two options. The first one is password, and the second one is secret. So I'll choose password for this example, and lastly, the password we choose. Can I identify the privilege here? To understand this, just put a few letters of the keyword PRI right here and press Tab. So if it's completed, that means the word is allowed here. If it wasn't completed, I'll just need to identify privilege as a separate command. So just delete PRI and hit Enter. So now we created the user Cisco1 with the password 12345. To identify privilege, as we've seen before, just type username Cisco1 privilege 15. Type exit and hit Enter to exit the config mode. And look at that. You'll see that we have an information message which says router has been configured. Okay, now let's go to Kali and try to gather the router configuration as a pen tester or ethical hacker. Open a terminal screen and run MSF console. So we've already seen these before, so I'll just keep it fast. Search for Cisco config keywords. Use the auxiliary module. Show the options, and now set the options. Community. Our host as the target router. Let me ping the router. Okay. Output directory to save the result. I'll choose to save it to the desktop. Our port is okay, and the other options are good in their default. Now we can run the module. Wait. The option is our hosts, not our host. I set the our hosts option. So let me run the module once again. Okay, so that'll do for now. The execution of the module completed, and the output file, which is the config of our router, has been created. Double-click to open it. And we have here the configuration of the router. So scroll down a bit, and here's a user we created just a couple of minutes ago, Cisco1. As we already know, the password is stored as clear text in this method, so we can see the password clearly. Now let's go one step further, shall we? I'll go back to the router console and go into the configure terminal mode once again. Type in service and put a question mark to see the service options. There is an option here, password encryption, to encrypt the system passwords, so let's use it. Exit from the configuration mode to let it rebuild the configuration. Now, we'll activate the password encryption. So let's go on back to Kali and grab the router configuration again. We already know how to run the auxiliary module, so just type run to run it. The output file is created. Double-click to open it, scroll down a bit, and here are the users. As you can see, the password is stored encrypted now. Excellent. So, does that mean it's okay now? No, absolutely not. Because the algorithm used to encrypt the passwords is very weak, which only takes a few seconds to crack. So now I'll copy the encrypted password, open a web browser, Google Cisco password, paste the hash, and search. I'll just click on the first link, which says Cisco Password Cracker. Now, be careful where you visit while studying hacking. You might just go face-to-face with some harmful websites, and I want to strongly caution you against that. So I'll paste the password hash here and press Crack Password. Oh man, it took less than a second to crack it. So what should we do to protect the passwords? Now we'll go another step further. I am back in the console of the router again. Enter the configure terminal mode. Now I'll create another user and let me use the secret method now. Type in username. Let the username be Cisco2, secret, and the password. Press enter. So identify the privilege. Username Cisco2, privilege 15. Exit the configuration mode, and the config is saved. Now let's go back to Kali and run the auxiliary module once again. So I'll delete the previous output file first. Okay. The output file is created. Double-click to open it and scroll down a little. The new user is here, Cisco2, and as you can see, the password is now stored as a Linux-like hash value. Do you remember Linux hashes inside the shadow file? They are the fields separated by the $sign. The first field is the type of the hash algorithm. The second part is the salt, and the rest is the hash value. Now we can say it's more secure. So although we stored the passwords with a strong encryption algorithm, it's still not safe to let just anyone access the password hashes because they're still open to the offline password cracking attacks. So it's possible to identify access control lists for the communication services such as SNMP, SSH, and Telnet. With these access lists, we can decide who can and cannot connect to the services, then close the services for everybody else. So there are two types of access lists, standard and extended. Let's have a look. We can see how we can manage the access to the router. So once again, we're back in the network we created by using GNS3. All the devices are still active and running. That's always a good sign. Open the router's console and enter the config terminal mode. Access list is the keyword to create and configure access control lists. So put a question mark to see the options. The number here decides the type of the access list. We'll make an example of standard access, so just put a number between 1 and 99. I'll just put 2. A standard access control list either denies or permits source IP addresses. In addition to source IP addresses, an extended access control list can also deny or permit based on destination IP addresses, ports, and those services as well. Question mark again, and these are the options. We can either deny or permit a connection request. So let's decide who to permit first. Question mark to see the options, okay? We can put a pattern here, so the computers matching the pattern are allowed. If we use any here, that means we permit all computers except ones which are identified by the deny and the access lists. Alternatively, we can permit directly to any specified computer. So here I'll use host as the option and let my colleague access to it. So let me look at the IP address of the colleague, 10.3. I want to deny all others. So access list 2 deny any. Now, the next thing we have to do is go to the line VTY and apply this access list to the interface. Good, so type line VTY 04 to enter line config. In the line config, we'll use access list command. Number of access lists first, and now a question mark to see the options. And look at that, there are two options, in and out. Now, since we're going to be telnetting into the router, we're going to use in, exit, or Control-C to exit from the line config mode. Now, I want you to see the running config, so type show run. And here is the running config. So scrolling down, I'll show you the access list and make sure that everything's right. So here it is. And yeah, as you can see, we have our access list 2 to permit Kali and deny any other host attempting to make a telnet connection. Now let's test whether the access list works as intended. So back in my network, I have other VM machines like Kali. One of them is OWASP BWA, as you know, and its IP address is 10.4. First, I want to check if the network is okay and OWASP sees the router. So ping 192.168.10.1. And sure enough, we have the replies. Now, I want to create a telnet connection to the router. So type telnet and the router IP. Hit enter. Connection is refused. Well, that's what's supposed to be, right? That means the deny part of the access list is working properly. What about the permit part? So go to Kali in terminal screen, telnet into the router, and as you can see, we can telnet into the router. The request is not refused, and we are allowed to telnet from Kali. So to double check, I'll run an nmap query to check whether the telnet port of the router is open. And yes, of course it is. SNMP security is another important point of network device security. First of all, you should check whether access to devices has been restricted by access control lists. As mentioned before, SNMP has 3 versions. In version 1 and 2, packets are transmitted as clear text, so the traffic between the client and the server is visible for the third parties who listen to the network traffic and learn the SNMP community name. In addition, there's just no authorization mechanism. SNMP v3 was developed due to the weaknesses identified in the first 2 versions. It has encryption and authorization features, but it does not have a mechanism to secure the community name. Port security is a feature that can help secure access to the physical network. We've been using the Cisco switch and router throughout the course, so I'm going to explain the port security on Cisco devices. Cisco IOS is the operating system of Cisco routers and network switches. And it has the port security feature, which can be used to restrict the MAC address of the devices that connect to each of the physical switch ports. Cisco Port Security can help to restrict the MAC address or addresses that can connect through a switch port, restrict the number of MAC addresses that can connect through a switch port, set aging of the MAC addresses registered. It can also set the action to take when there is a violation detected. So there are 3 action modes in case of a violation. Protect drops packets with unknown source addresses until you remove a sufficient number of secure MAC addresses to drop below the maximum value. Restrict drops packets with unknown source addresses until you remove a sufficient number of secure MAC addresses to drop below the maximum value. And it causes the security violation counter to increment. Shutdown puts the interface into the error disabled state immediately and sends an SNMP trap notification. This is the default action. So here I'll put up some port security usage examples. The first 3 lines are to be able to start using port security function to begin with. Enter the configure terminal and the interface you want to configure, and then set the port mode as access. The default port mode is dynamic desirable, and you cannot configure a port in dynamic desirable. If you use port security without any parameter, it enables the port security on the switch port with the defaults. And the defaults are 1 MAC address allowed. First connected MAC address is set statically, and disable port if there is a violation. So if you use the function with MAC address parameter, only the server with a specified MAC address is allowed. Max parameter is used to set the maximum number of MAC addresses allowed on the secure port. If you don't set the max value, the default number is 128. And you can identify how long will the port security roles be active using the aging time parameter. And the value, as always, is in minutes. So listen, I want to thank you for choosing us, and I hope to see you in another course. You might just have learned something. See you next time.